Are we alone in the universe?
There are approximately 2 trillion galaxies. So I personally believe that there are other intelligent civilizations out there in the universe. Let's say we pick up some radio signal from a distant alien civilization. Now what? They are 300 light years away. We are effectively alone. Space is big. If there is some advanced intelligent species that has been around for 1 million years, they already know we're here. But I also don't believe that science is equipped to answer all the questions. Like, what happened before the universe? What is love? What is time? How do I live a just life? I don't look to science to answer those questions.
Do you believe in God? There's been recent news in front of Congress, and there are multiple whistleblowers that are discussing UAPs and potentially non-human biologics that are in the possession of the US government. Obviously, I'm not going to ask you to speak on the political nature of whether or not we possess this technology or these beings, but I'm curious just from an astrophysicist's perspective, you personally, but also what's believed within the community, are we alone in the universe? And how would you go forward in trying to answer that question?
Yeah. First, I'd like to say this phrase, like non-human biologics, is very interesting because that's a cow. And so, if the U.S. government owns a herd of cattle, then they are in possession of non-human biologics.
That's a great point. What does that really mean, non-human
It means
biologics?
nothing. It's a meaningless term that sounds cool.
Yeah, it does.
Just say aliens. If you mean aliens, just say aliens. Like, don't try to hide it under weird jargon terms. Just say aliens. Space aliens with big eyes and gray heads.
Sure.
So
that's what people mean when they say that.
Yeah. So just say it. Just say what you mean. Quit beating around the bush. Like, are we alone? I don't know. I have two minds about this. One is we have absolutely zero, and I mean zero, evidence for any life, intelligent life, bacterial life, somewhere in the middle life, any life whatsoever outside of the Earth than what we know. None of the planets in the solar system, we have found any evidence for life. We have not found any evidence for life in any radio signals washing over the Earth. We have not found any evidence for life orbiting other stars. We have zero evidence so far. On the other hand, it's a big universe out there. We are one planet orbiting one star. Our Milky Way galaxy has somewhere around 300 billion stars. The estimate for number of planets in the galaxy range on the low end from 100 billion and on the top end 10 trillion. It's a little bit. We've got some work to do to pin that one down. In the observable universe, there are approximately 2 trillion galaxies, each one of those with hundreds of billions of stars. So life happened here. Obviously, life isn't super common in the universe. Otherwise, we would have met someone by now. But to think that we're alone and that this entire universe is just for us and we are the singular example of life and intelligence and self-awareness in the entire cosmos, in all these 2 trillion galaxies existing for nearly 14 billion years, seems like a stretch. So I personally believe that we're not alone, that there are other intelligent civilizations out there in the universe. We have not had any evidence for them yet, but they've also not visited us because we're really boring.
Yeah. So what you're basically explaining is the Fermi paradox, right?
The Fermi paradox is interesting because I actually don't view it as a paradox. And I think the Fermi paradox was interesting and engaging when it was first proposed around 50 years ago. I don't think it's a paradox anymore.
And can you basically explain it, but could you just paraphrase what that is?
Yeah, the Fermi paradox is this. If life happened here, then obviously the universe is capable of creating intelligent life because it happened at least once. And the universe tends not to do things in small measures. If it happens once, it happens a bunch of times. So therefore, we're not alone. There are other intelligent civilizations that currently exist or have existed in the past. And intelligent civilizations can do things like build rocket ships or send robotic probes or just travel or send radio signals or do whatever to make their presence known in a relatively short amount of time. Let's say it takes 2 million years for an intelligent civilization to completely colonize an entire galaxy. Our galaxy has existed for 9 billion years. So that's a lot of chances. So where are they? This is the paradox. If life is here, then life is likely common, and yet we find no evidence for life. That is the Fermi paradox.
Right. And why don't you see it as a paradox?
I don't see it as a paradox because we humans, as smart and capable and advanced as we are, have a very, very hard time appreciating truly astronomical scales. We can say numbers all day long. We can say the nearest star is about 4 light years away. We can say the Milky Way galaxy is 100,000 light years across. We can say our universe is 13.77 billion years old. These numbers are easy to say. They're a lot harder to comprehend on a human scale. I live in New England. I live in Connecticut, and people think traveling to New York City is such a beast. It's so very far home. Wow, you're going to New York City. Wow. Okay. The distances between stars, individual stars, is literally unfathomable to human perception and the way our brains are wired. The nearest star, Proxima Centauri, about 4 light years away. If we were to send one of our spacecraft to it, like the Voyager probes or New Horizons, one of our spacecraft that is on a solar escape trajectory entering or has entered interstellar space, none of them are aimed in the direction of Proxima Centauri. If they were, these spacecraft, which are traveling at 35,000 miles per hour, would take nearly 50,000 years to reach the next nearest star. That is approximately how long humans have been a species on this earth, 50,000 years. And that's our nearest neighbor.
Yeah.
Our most powerful radio signals that we have blasted out into space, and not just like the television broadcast. I'm talking about signals that are intentionally meant to be received by aliens using our most powerful radio antennas, pumping all the power in to blast a signal. By the time they reach Proxima Centauri, our nearest neighbor star, those radio signals are so weak they cannot be distinguished from background noise. Civilization, there could be 1,000 intelligent species in the galaxy right now. Each one of these civilizations could have lasted for millions of years, and they are essentially invisible to us. Stars are so far away. Galaxies are so big. Cosmic time scales and space scales are so large that I believe that we are not alone, that there are other intelligent species out there in the galaxy and the wider universe, but we are effectively alone. We are separated by vast gulfs of space and time that make us essentially an island.
Yeah. Yeah, I guess the thing that always puts in perspective for me is the idea of 4 light years away. You'd have to be moving at the speed of light, which is virtually impossible, for 4 years.
100% impossible. You can't. You just can't. And even then, even light takes 4 years to make it.
Right. And that is as fast as it can go. It's 4 years.
Yeah.
Yeah.
Although from relativity, there's this weird thing in special relativity, which I feel like gets underappreciated. Everyone's trying to cheat the speed of light limitation, which stop trying. You can't. We checked. But relativity says, and this is Einstein's special theory of relativity, which tells us about the relationship between space and time. And it tells us that space and time are connected. When physicists talk about space-time, we're not just using some clever jargon word that looks good on a poster. We mean we live in a 4-dimensional fabric. We live in a 4-dimensional universe, and it's impossible to talk about space without talking about time and vice versa. And this has many, many consequences. One of the consequences is that the faster you move in space, the slower you move in time.
Right.
As you approach the speed of light, you will age slower than the rest of the universe. You can run the numbers, because that's what physics is. You can run these calculations, and let's say you were to go in a spaceship that travels a decent fraction of the speed of light, like 99.999% of the speed of light.
Pretty good.
You could aim for the center of the Milky Way galaxy, which is about 25,000 light years away. From observers stuck on Earth, it will take you nearly 25,000 years to reach the center of the Milky Way galaxy. From your perspective, it will take a couple decades. You can cheat space and time. You just have to go really fast.
Now, I've heard this in relation to time travel, which is very interesting because, obviously we're time traveling right now.
Obviously, 1 second per second.
Exactly. So the idea of expediting forward time travel is relatively possible. And I think it was Brian Greene that explained this. But effectively, if you're on Earth, you could blast off, 50,000 light years or whatever, going super fast, speed of light, and you go for 50 years. and then you come back for another 50 years. So let's say time that's in human time. So let's say 20 years out, 20 years back.
According to a watch on your wrist.
On your wrist in the craft. If you came back to Earth, it could be 100,000 years later.
Exactly.
You would come back to an Earth that is 100,000 years older. All the people that you know for generations have been dead, but you are still within your one lifetime.
Which could be a blessing or a curse. It depends on your particular perspective and situation to leave everyone behind by thousands, tens of thousands of years. All you have to do is go really fast. And this isn't just a hypothesis. This isn't just theory. This is verified experimental reality. We can measure this. We can put atomic clocks inside of jet aircraft and buzz them around the world. And they're going not nearly the speed of light, but they're going fast enough. And our atomic clocks are sensitive enough that we can compare them to an atomic clock that stayed on the ground, and we can literally see the difference.
Yeah, that's fascinating. You could send two twins. One twin goes to the International Space Station, one stays on Earth, and they will be different ages.
Exactly.
That's fascinating.
Measurements of time and space are not uniform throughout the universe. Nobody can agree on measures in time or space. This is relativity. This is what is relative, which is measures of time and space.
Right. So now when it comes to aliens, and I guess when we're talking about aliens, we're talking about sentient, conscious, intelligent life.
The cool aliens. Like, we might find some plankton on Titan or Europa, and that'll be cool, but we want to talk to someone.
Right, exactly. Yeah, and those things, I guess, to me are like, everyone should basically be on board with that. The idea that there's, an amoeba that exists on some far exoplanet seems very possible.
Absolutely. And I actually suspect, or at least hope, that in the next few years, if not decades, we will find evidence for alien life forms of some kind, either in our solar system, which there are a lot of very interesting places where they might crop up, or around some other star.
Right. What are the places that you mentioned that they might crop up?
Yeah, so for a long time, we thought Mars might be a home for life because it used to have a lot of water. We can see the evidence for that water everywhere. Mars used to be wet, had lakes, rivers, streams, oceans, water vapor in the atmosphere, the whole deal, about 3 to 4 billion years ago, at the exact same time that the Earth had water, lakes, rivers, streams, oceans, water vapor. And at that time, life was getting started on Earth. And Mars had the exact same conditions. It's reasonable to suspect that if life can gain a foothold here, it could possibly gain a foothold on Mars. Now, Mars is not so wet anymore. It dried out billions of years ago.
Do you know why it dried out?
Mars had a birth defect. Mars had a birth defect, which it was too small. So the Earth has a force field, a literal force field surrounding it. It's our magnetic field. It's generated in our core. The core of the Earth is molten and made of metal and spinning really fast, and this generates a very powerful magnetic field, the most powerful magnetic field in the inner solar system. This magnetic field protects our atmosphere. It protects our atmosphere from the sun. The sun is constantly emitting this stream of high-energy particles. We call it the solar wind. It's everywhere. It hits the Earth, and our magnetic field deflects these charged particles.
Oh, wow.
Billions of years ago, the interior of Mars was molten. It had a core, it had a magnetic field. But then Mars was too small and it cooled off. And its core solidified, the magnetic field went away, and this solar wind blew away the Martian atmosphere like dandelion seeds.
Wow.
And it died.
Fascinating. So I guess when people look at like the aurora borealis, so they look at, the northern lights, those are basically plasma flares from the sun that are getting deflected off. Is that?
Exactly. That is the solar wind impacting our magnetic field. They get trapped by our magnetic field and funneled into our poles where they plow down into the atmosphere, and we see them as the aurora.
Oh, fascinating. That is wild. And our magnetic field is created because of the molten core.
Exactly. And if you don't have a molten core, it's very difficult to generate a magnetic field.
Oh, wow.
And so Mars was too small. It cooled off, lost its air, lost its oceans. The oceans boiled in the vacuum that was left behind. And maybe life found a way to survive, maybe buried under some rocks. We don't know. So we're digging around Mars right now. There are rovers right now that are searching for evidence of at least past life. But the likelihood of life being on Mars right now is pretty slim. But Mars is not alone. The key component for life as we know it is liquid water. Liquid water is how life evolved on our planet. We thought for a long time we were alone when it came to liquid water in the solar system. But there are some secrets out there in the outer solar system. The orbiting Jupiter and Saturn, some of the moons have icy crusts and water ice, like ice crusts. Underneath that water ice, which can be anywhere from 10 to 100 miles thick, we have recently discovered globe-spanning liquid water oceans. So Europa, Enceladus, Ganymede, Callisto, these worlds we believe in, even Titan, we believe have subsurface, subterranean liquid water oceans, each one with more liquid water than the Earth has. Now, these oceans will be completely blocked from the sun. They're buried under dozens of miles of ice. But it's liquid. It's cold, but not freezing. Now, if you can get the other ingredients for life, besides liquid water, carbon, oxygen, nitrogen, phosphorus, hydrogen, the basic components of biochemistry, these worlds might have it. We don't know yet. We don't know.
Wow.
But if there's a place for life in the solar system other than the Earth, it's probably buried under the ice of the outer moons.
And would those be considered, those are moons?
Yes.
Okay. So those would not be considered cool planets?
No, these are in one of the reasons we never like thought of life out there in the outer solar system was it's so far away from the sun. We have liquid water here on the Earth because we're nice and close to the sun. Mm-hmm. Mercury, the innermost planet, does not have liquid water because it's too close. It's too hot. Asteroid belt, Jupiter, Saturn, those don't have liquid water because they're too far. Water just freezes. But these moons are warm on the inside. Their cores are actually molten and their surfaces are frozen solid. But in between those layers is the sweet spot where water can be liquid.
Wow, that's interesting. Now, is a magnetic field a prerequisite for a planet to create the elements of life?
Maybe, maybe not. The conditions necessary for life are a bit unknown because we have exactly one data point.
Right.
And so we can list the things that Earth has. We're big, but not too big. We have a molten core. We have plate tectonics. We have liquid water on the surface. We have a nice thick atmosphere, but not too thick. We have a moon. We have a magnetic field. We have a nice pleasant sun. Like, we can list all these things. We don't know which one of these are absolutely critical for life or maybe not critical at all, or, you know, it doesn't matter if we have a moon or not. We don't know. So it seems that magnetic fields are important for protecting planetary atmospheres. That said, Venus, the next planet in from the Earth, closer to the sun, does not have a strong magnetic field at all, and yet it has an incredibly thick atmosphere. It actually tilts the other way. Its atmosphere is like 100 times the pressure of the Earth.
Extremely like sulfuric.
And also it's nasty. It's mostly carbon dioxide, and then what's not carbon dioxide is sulfuric acid, aka acid rain. It's just a nasty place. But it doesn't have a strong magnetic field, but it's big enough to retain a nice thick atmosphere.
You saw the photos from the rover recently on Venus, right?
On Venus,
yeah,
the last landing on Venus was in the 1970s.
Oh, really?
Yeah, so I don't know where you get your news, but it might be a little out of date.
Okay, can I check really quick? Because I saw this recently and I was like, wait, what? And
was it from Mars?
I don't know. Let's find out. Okay. Now I'm too curious. This literally was this was very recent. I'm going to assume that I'm probably out to lunch here, but let me double check.
You never know.
Dude, I think I got duped.
I'm sorry. Well, that's what you get for reading Reddit.
Dude, I got duped.
Here's an artist's impression from a news article a couple days ago.
Dude, this is the one I saw, and apparently
that's super old.
What is this from?
That was from a Soviet Venera mission. They launched a whole bunch of landers towards Venus, and most of them failed. Well, all of them failed, but some lasted longer than others. I think the longest any probe has lasted on the surface of Venus is 15 to 20 minutes.
Okay.
The problem is not just the overwhelming crushing air pressure. It's also the temperatures. Surface temperatures on Venus are around 800 degrees Fahrenheit. So not a pleasant place at all.
Interesting. And that was in the 80s.
That was in the 70s.
So is it even worth sending something there now if it's just going to vaporize in an hour?
Well, it depends on what you mean by worth it, because you can always find at least one scientist who finds it interesting. And there are a lot of people, there are a lot of planetary scientists who are very interested in Venus because it's very similar to the Earth in terms of size and composition, but at a very different trajectory in terms of evolution of the planet and the atmosphere. And so by studying Venus, we can hope to learn about the Earth. And I don't know, we're just kind of generally curious about the planets and would like to learn more. And there have been a couple successful NASA proposals for new missions to Venus, especially ones that like float around in the atmosphere. I believe those have been delayed because of various cost overruns and mismanagement at JPL.
That makes sense. Interesting. So yeah, this idea that aliens are coming from far away planets, moving at the speed of light, intelligent life, because we've established there potentially could be, residual amoeba or even existing bacteria. But let's say intelligent life coming to the Earth. Do we have enough detection on Earth for things that are entering and leaving our actual atmosphere to detect on a global scale if there was a craft or something coming in and out?
Yeah, in principle, yeah, because we actually, we detect meteors all the time.
Right.
In fact, the International Space Station, one of the experiments on the International Space Station is to look for meteors streaking through our atmosphere. And there are amateur sky gazers, amateur astronomers, just enthusiasts who are constantly monitoring and mapping anything that enters our atmosphere. And the thing is, if you're coming from space, you are going to be moving very quickly, tens of thousands of miles per hour. And then when you land on the ground, you're not going to be moving quickly anymore because you're on the ground. And so going through the atmosphere is always going to be a somewhat violent process. You're going to light up, you're going to be seen, you're going to be viewed, and there's just no way around it. That is just how orbital physics works. And this is why meteors light up. This is why tiny bits of dust always light up when they enter our atmosphere and we see it as a shooting star. So between professional observation and amateur observation, obviously we don't have the whole sky covered 24/7, but we do have a good fraction of it.
Mm-hmm. What percentage would you say, if you had to guess, in terms of like general coverage, like from the government, from amateurs?
Oh, that I actually have no idea, because there are also satellites that are constantly monitoring the Earth for other purposes, or the atmosphere for other purposes, and happen to catch meteors, streaks. I have no idea. Somewhere between 10 and say 60%. But that's just a pure guess.
Sure. I mean, yeah, because it just seems interesting if these things are moving in and out. Obviously, the idea is that they would operate with, different technology and more advanced technology, but they're still bound by the same laws of physics that you and I are bound by.
Right. They may have a better understanding of physics, just like we have a better understanding of physics than we did 100 years ago. Mm-hmm. And we have many devices that our ancestors would consider miraculous or magical, simply because they didn't have the same grasp of the physical world that we do. But there are some things we know for sure. And there are some things we know, all knowledge in physics, all knowledge in science is provisional. There can always be a piece of evidence that can change our mind. But there are some things that we know that we would take a lot to change our mind about and have not changed in a very, very long time. Things like the speed of light limitation.
Right.
And so, but no matter what, even if aliens have a more advanced understanding of physics, they still live in the same universe. They still interact with the same universe that we do. They still emit or absorb photons, or they use the strong gravitational force. Even if they have a more sophisticated understanding, it's still the same universe. And they must be detectable in some way.
Yeah, that's interesting. So if they are coming in and out of our atmosphere, they're likely detected. And if they're detected, it's an intentional, non-disclosure from the government or some other force that's not wanting these things to be out.
Which is hard to believe. The whole conspiracy angle. Has the government ever kept a secret for long, and with no whistleblowers, with no one coming out with primary evidence? Yes, our government is capable of maintaining secrets for some amount of time, but eventually the truth comes out. Mm-hmm. And the scale of the cover-up involved would require involving thousands of people, especially if you're talking about like outrageous claims like capturing downed spacecraft and studying them and housing them. Like, there are a lot of human beings involved in that process, and it would require every single one of them to participate in this conspiracy without saying anything. And then what we have with the recent whistleblowers and the House hearings, none of these people who are, quote, blowing the whistle are primary witnesses. None of these people have or are even claiming to have seen an alien spacecraft or a non-human biological.
Right.
All they say is that they were told of the existence of these programs. So I want to know, like, okay, why aren't we talking to those people?
Right.
Like, if you heard it from Jimmy down at the base, let's talk to Jimmy. But you're not telling us who you heard it from. You're just saying you heard it. So that's like secondhand whistleblowing.
Right.
And without any like primary evidence, if you say these programs exist, well, then haul like an alien hand in front of Congress. Like, let's get this over with. Quit beating around the bush. If you've got evidence for it, go ahead, change my mind. It's the beauty of being a scientist is you're free to change your mind as soon as there is new evidence.
Interesting.
But just saying that there's evidence and not producing the evidence isn't good enough.
Right. Yeah. I mean, now we're just in speculation land, but I wonder if it is like a geopolitical tactic, right? Like that these things are being brought forth in front of the government to kind of intimidate other countries, to maybe try to flex reverse engineered energy or technology that we have.
Yeah. Who knows?
I'm curious what the motivation is.
Or it's all just a stupid waste of time.
Right.
I mean, have you met your particular representatives in Congress? You know, they can be very smart in some ways and not so smart in other ways.
Sure.
And maybe it's just a giant waste of time and there is no motivation. Maybe there is no grander purpose. Maybe it's just a bunch of people like guessing.
Do you think there is a risk of sending radio waves out into space and like trying to find other life? I know obviously there's been different initiatives in the past where, you know, sending shuttles or sending technology packs. I've seen like, you know, Da Vinci's etchings that have gone off in shuttles, I guess. Is there a risk with that we're alerting other people, this idea that we're shouting in the woods?
I believe there's absolutely no risk whatsoever for a couple reasons. One, we are effectively alone. The distances in time and space that we're dealing with, even if someone were to pick up one of our signals. Or let's reverse that. Let's say tomorrow, the SETI, the Search for Extraterrestrial Intelligence, we pick up some radio signal from a distant alien civilization, like 300 light years away. And they send a message that is unambiguously artificial. We know it was created by some intelligence. Okay. Now what? They are 300 light years away. Even to send a response to them would take another 300 years for them to get it. And so that is 600 years from the moment they sent the signal. Space is big.
Yeah.
Even if an alien were to find out that we're here, what are they going to do about it? And let's say, let's take that leap. Let's say they have achieved some mastery of physics that we don't understand, and they are capable of traveling throughout the galaxy very easily. What do we have here that they don't already have? You want water? There's plenty of it everywhere. It's the most common molecule in the entire universe. Water.
Interesting. Even on, obviously in our solar system, it's fairly rare. But in the other exoplanets and farther solar systems, it's more likely.
Yeah, most water is frozen.
Right.
But it is the most common molecule. You want water, you got it. You want gold? There's more gold sitting in an asteroid called 16 Psyche than there is accessible on the crust of the Earth.
Diamonds.
Diamonds, same deal. You want diamonds? You can just make diamonds. We can make diamonds in a laboratory right now. And if you're an advanced alien species, you might as well have a blinged out spacecraft, because if you can do that, you can make diamonds. You don't care. You don't need to dig diamonds out of the ground. It's stupid. You can just make them. There's nothing here in terms of natural resources that are not orders of magnitude more abundant other places in the universe. The only thing we have going that sets us apart, that is unique, that is worth investigating, is our culture. And if they've got our YouTube videos by now, I don't think they're coming by anytime soon.
Our TikTok dances, you don't think that's going to pull
maybe
them
the
in?
TikTok, that might pull them in. There's this trend going around this quadrant of the galaxy. So there's nothing here. There's no point in it. Why waste your time visiting some planet to gather natural resources that are so much easier to just gather everywhere else? And then, yeah, we're alone. There's nothing worth grabbing or taking here. And the universe is a big place. And if aliens are watching us, if there is some advanced intelligent species that has been around for 1 million years, they already know we're here. They don't need our radio signals. They know we're here because if we figured out a trick for searching for life on other planets, then likely they have figured out the same trick. And the trick is this. This is how we're hunting for life on other planets. You wait, you stare at a star. You stare long enough, and if it has planets around it, and if those planets happen to line up just right, like the plane of their orbits, then every once in a while that planet will cross in front of the face of its star from our point of view. And from our point of view, what will happen is we'll see the star and it'll be nice and bright, and then that planet will cross in front of it and it will block out just a tiny, tiny, tiny part of that light. The star will appear to be a little bit dimmer. And then the planet will leave as it continues on its orbit, and the star will resume its normal brightness. This is called the transit method. And with this method, we've identified nearly 5,000 planets outside the solar system. This is how we do it. We can take it one step further, because when that planet crosses in front of that star, just a tiny bit of that light from that star passes through the atmosphere of that planet before reaching the Earth. This changes the light. If there are elements in that atmosphere, it will absorb or emit different wavelengths of that light from the star. And depending on how much of those elements are there and what mixture of elements, you'll change the light from the star in a different way. We use this technique. We have already used it to identify elements in alien atmospheres, exoplanet atmospheres. And this is how we're searching for life. We are looking right now actively, the James Webb Space Telescope. This is one of its missions. And then there are follow-up telescopes that will continue this to look for, say, an abundance of oxygen in a planetary atmosphere. The Earth should not have this much oxygen in its atmosphere. It's here because of photosynthesis, because of the byproduct of life. If we look at an alien planet and there's a lot of, say, methane, a lot of carbon dioxide, and a lot of oxygen, there's probably life on that planet. This is one of the primary goals of NASA now, NASA science. So if we can do it, aliens can do it. And there's been an abundance of oxygen on our planet for over 3 billion years. They already know that this planet is alive. They already know that life has changed the character of this world. They're already watching us.
Interesting. Now, from a physics perspective, this is obviously that this theory is predicated on the idea that, life is starting from the same building blocks. Is there any evidence to support that life can start with different building blocks?
Oh yeah, this is wild. So everything that we're searching for in terms of life elsewhere in the universe is based on the assumption that the life is a lot like us.
Right.
Uses liquid water as a solvent, uses carbon to build structures, et cetera, et
There's
cetera.
that singular data point that you mentioned before.
Exactly. It is perfectly valid to assume that life can take other forms. We even have a hard time defining life, even with the biochemistry here on Earth and the dividing line between life and non-life. We already have a tough time with that. So it's easy to imagine that there is some form of life that can take advantage of alternative biochemistry. On the other hand, we don't know what that looks like. We don't know what to look for. If we see some strange chemical reaction on some strange rock, unless it's a chemical reaction that we recognize as biochemistry, then we can just say, well, it's just a rock being a weird rock. We can't say it's, we have a lot harder time saying it's alive.
Mm-hmm.
That's why the focus is on Earth-like life, because we know what we're looking for.
Right.
That search does not exclude the possibility that life could take other pathways or take other forms, as exotic as you want, but we wouldn't know it if it were staring us in the face.
Mm-hmm.
As an example of this, the largest moon of Saturn is called Titan. Titan is the only moon in the entire solar system with a thick atmosphere. Titan is relatively small and smaller than our own moon. And it has a very, very thick nitrogen-dominated atmosphere. Its surface is frozen solid. Ice, again, a water ice crust. But there are liquids on the surface of that world. There are lakes, there are rivers, there are streams, but these are not lakes and rivers of liquid water. These are lakes and rivers of liquid methane. There's an entire hydrological cycle on Titan, operating at temperatures nearly 200 degrees below zero, not with water, but with methane, like propane, nearly gasoline.
Mm-hmm.
Okay, that's not water, but it's a liquid. There could be a form of life in those seas of Titan, operating at 200 degrees below zero, using not water as a solvent, but methane as a solvent. And there are active research programs right now to try to understand what that biochemistry might look like. How is energy stored and released? How is information copied? Could there be an alternative pathway to life on Titan? We don't know. There are missions right now being designed right now by NASA called the Dragonfly mission that will hopefully fly to Titan and fly around the atmosphere of Titan and pick up samples and look for life. But in order to recognize it as life and not just weird Titan chemistry, we need to understand how that kind of biochemistry might lead to life.
Interesting. Now, this will be the last question I ask you on this topic specifically, but if there is some type of governmental disclosure, right? Let's say the government is like, hey, this whistleblower is completely correct. We do have non-human
Sorry,
whatever.
folks. Yep.
Do you think it'll split the physics community? Do you think there will be people that are saying, no, this is not true, it's not possible? Do you think the physics community will fall in line? Do you think it'll politically fracture that world?
I don't think so. I think evidence is evidence, and we all have our disagreements. We all get into shouting matches at conferences, but we all respect the evidence. That is our training. Mm-hmm. That nature is the ultimate arbiter of our beliefs, and that our beliefs are always update to change and revolution with new evidence. If the United States government says, you know what, okay, you got us. Aliens have been visiting the Earth for a very long time, and we've been capturing them and dissecting them, and that's why you have cell phones now. You're welcome. And here it is. Here's the body. Here's the spacecraft. Go ahead, poke around. We don't care anymore. Okay, evidence is evidence. We get over it. Okay, everything I said about us being effectively alone and we're not worth visiting was wrong. Mm-hmm. Okay, I've been wrong before. I'll be wrong again. And now we get to go on a brand new journey.
Interesting. Yeah, I'm so curious about that. Like, if there would be people that would say, no, there's no way, or that if the people in the physics community would be dissenting. But it seems like generally most people would be like, hey, if it checks out and
if there's
some explanation.
If I can poke the alien, do we get to go in line to poke the alien?
Yeah.
Whether I'm like, is it squishy?
You got to pay for it, I think. Yeah. I don't know what the fees are for
Well,
that.
maybe they put it up in the Smithsonian. You can get it for free.
Oh, that'd be cool.
They just put it up in the National Mall or something. You just line up along the Potomac and you get to squish the alien.
Do you think there's ever a reason to go back to the moon? Like, you personally, are you like, oh, that would be a fruitless mission. We've already done it.
This is not an easy question. You're asking very nuanced questions, and there is no right answer to this question. Scientifically, there's a lot we don't know about the moon, and there's a lot we can learn from the moon about the formation of the Earth, the formation of the solar system. It's a time capsule that's sitting right there. Human crewed missions are always much more difficult to justify because they are a lot more expensive than robotic missions. On the other hand, crewed missions are much more capable than robotic missions.
Sure.
The Apollo missions that went to the moon, they spent a total of, I forget the exact number, but it's somewhere around 100 hours on the surface of the moon in total.
Yeah.
Across all the missions. And that alone generated somewhere around 500 scientific papers.
Wow.
Just from the evidence that the data they were able to gather. That is more than all of the robotic missions who have spent months and years cumulatively on the surface of the moon combined. So humans are the best machines for gathering information and gathering data and doing science. There is nothing that beats the speed or agility or decision-making capability or creativity of a human actually doing field work. On the other hand, it is ridiculously expensive to send humans to the moon. So from a purely scientific standpoint, there are arguments back and forth. I generally lean towards if we can send people back, let's send people back because that's super cool. And what use is having a civilization if we can't do fun stuff like send human beings to other planets?
Right.
There are other motivations, trying to establish more permanent presences on alien worlds, on the moon, on Mars, on asteroids. That's a lot harder and honestly a lot bigger pill to swallow, because setting up actual independent or quasi-independent bases where humans can live and work is much more expensive and much harder than we can imagine. But that doesn't mean it's not worth doing.
Mm-hmm. Yeah, I'm curious if there's different technological restraints now, because the last time we went was 69 or later than that perhaps, but
last mission was 76, I think.
Okay. So, I mean, it's been, almost 50 years.
It's been a minute.
Yeah. And I wonder, are there any physiological or astronomical changes that are going to make it more difficult or more simple to do? It seems like our technology has gotten so much more robust since that time that it would be easier, but that's just from a layperson's perspective.
Our technology has gotten better. We are better at building spacecraft now. On the other hand, all the people that sent us to the moon originally are now either dead or retired. Mm-hmm. And so the unique skill set, not just to build a rocket and send it into orbit, but to design a lander that sends humans onto the surface of the moon and then return them. We have lost that knowledge generationally. If we want to do it again, and we're trying to do it again, we have to basically do it from scratch. Because we have blueprints, but blueprints don't contain all the knowledge that it takes to actually achieve a mission like this. There's a lot of knowledge that are locked up in human brains who are trying to solve problem after problem. And there's this conversation, then you figure this out. Let's adjust it here. And then, shoot, we didn't think of that. Now we got to try this. We've lost all that.
It just seems like such a mistake.
I think it was.
To lose that information, that knowledge.
It was. On the other hand, the Apollo missions were more successful than they probably should have been. They were much riskier. Now, in hindsight, we can tell that even with all the safety measures in place, even with all the rigorous testing, the Apollo missions were much, much riskier than we realized at the time. And the fact that we only had one accident, the Apollo 13 accident, was actually kind of a miracle. And the risk tolerance that we had in the 60s and 70s is a lot higher than our risk tolerance today.
Right.
And that if we're going to do it again, and we are going to do it again, it can't be as risky as the Apollo missions. It can't be as risky as the shuttle program. It has to basically work every single time, because there is this perception, real or imagined, but it's there, that the public has zero appetite and Congress has zero appetite for a failed mission and dead astronauts on the moon. So we have to get it right every single time. Right.
Yeah, that's interesting. There's obviously exogenous political factors at that time that propelled a lot of the fervor and the passion for those things
that aren't there anymore.
Right. Yeah, that definitely has cooled off. And the idea of people being stuck on the moon would be a major
horrendous.
Yeah, I mean, horrendous for a litany of reasons, but just to American space funding, I'm sure.
Exactly. Good luck galvanizing support if anyone can break out a backyard telescope and see the ruins of a failed mission on the surface of the moon.
I mean, this is kind of morbid, But if someone died on the surface of the moon, would they decay at the same rate as they would on Earth?
No, they wouldn't, because most decay on the Earth is driven by biology, by bacteria feasting on your flesh. When you die on the moon, you have your own complement of bacteria that are eventually going to eat, but eventually they're going to run out of oxygen, and they too are going to die. And then your corpse will just sit there.
Dude.
Yeah.
That's like Mount Everest type shit.
Yeah, basically.
Like where someone will just be basically preserved.
Yeah.
And so if someone, heaven forbid, were to die on the moon, a casual person could get a telescope and see them.
They may not see the bodies. You may need a rather large telescope for that, but they could see like the spacecraft or parts of the spacecraft.
Dude, that's wild. Yeah, I could see how that would be an issue.
That'd be a problem.
And that the whole world could see your F up.
Yeah, exactly. And of course, any mission to the moon is like the original Apollo missions were televised, broadcast. And if there's some mishap, if something goes wrong, there's no second chances this time around.
Right.
And so we have to be a lot more careful, which makes things a lot more expensive.
Yeah, I've heard that with the original missions, we got so lucky because we weren't necessarily aware of how much radiation was coming from like the Van Allen radiation belt. Have you heard this before?
There was a brief amount of debate. So the Van Allen radiation belts, when I talked about the solar wind coming from the sun, these are all charged particles like electrons and whatever. And our magnetic field deflects many of them, funnels many of them down into the poles. But some of them come in at just the right angle with just the right energy that they get trapped and they get just sent on this orbital path around the Earth, around and around and around and around. Eventually they leave, they get scattered, they fall into our atmosphere, they fly out into space, but then they're just replaced by more because the solar wind doesn't stop. So there's this radiation belt around the Earth, this stream of charged particles caused by our magnetic field called the Van Allen belts. There was a brief amount of debate about how strong these radiation belts are, but very quick calculations and observations showed that they're essentially nothing.
Interesting.
It would register as a vacuum.
Oh, interesting. Yeah. So even now, if we were to go, it wouldn't. I was under the impression that we weren't aware of how much radiation there was, and that now we realize that there's more than there was, or there was always the same amount that we realize now it was more risky than we did in the past. And so now that goes into like that actuarial situation where they're trying to assess risk.
The Van Allen belts do not pose a significant health hazard to astronauts. Also because astronauts have this thing called a spaceship, which is made of metal, which is very good at blocking charged particles.
Interesting.
They just bounce off the metal. But what is a danger for long-term missions. And so now we're talking about, say, long-term missions to the moon or even short-term missions to Mars. Mars is so far away that a minimum round trip is around 2 years.
Just to get there?
A round trip. So you need about 6 months to get there. And then you have to, but by the time you get there, Mars is on nearly the opposite side of the solar system. So you have to wait for our plans to line up again, and then you send the return mission back. So it's about 18 months total travel time and then 6 months on the surface of Mars. There is radiation constantly soaking the universe, not necessarily from the sun, from outer space, from distant supernova, from quasars, from high energy events that occur all throughout the universe. They soak the universe in something we call cosmic rays, which are not rays at all, but by the time we figured that out, the name Adele Ray stuck. These are charged particles, again, like the solar wind, but heavier. We're talking protons. We're talking helium nuclei that are traveling a significant fraction of the speed of light, like nearly the speed of light.
Wow.
Incredibly energetic particles.
Yeah, that's a lot of force.
It's a lot of force. Thankfully, they're very tiny. But what these particles can do is they can snip molecular bonds. They can slip in between your organs, in between your cells, and they can just blast through a cell and rip it apart. They can even blast through your DNA and snip apart your DNA. This is how radiation damages human beings by ripping apart your DNA, by ripping apart your cells, and cosmic rays are no exception. The longer you spend in space, the greater your exposure, your accumulated exposure to cosmic rays, the greater chance that they are going to cause some form of damage, especially to your DNA, that your body cannot repair. And that leads to cancer. And in the case of cosmic rays, the skin, the metal shell of a spacecraft isn't going to work. Because what happens is that the cosmic ray hits one of the molecules in the shell of your spacecraft. And the cosmic ray goes away, but it dumps so much energy that it creates a shower of subatomic particles that then rain through your spacecraft and rain through your body and cause just as much damage as the original cosmic ray did.
Wow.
This happens in our atmosphere all the time. Cosmic rays hit our upper atmosphere and strike oxygen or nitrogen, break apart into a shower that rains down on the ground. And it's estimated, this is a very rough estimate, that somewhere around 3% of all cancers that all living beings get are caused by cosmic rays hitting the surface of the Earth.
Wow.
Long-term missions to Mars, we have to figure this out. We have to figure out how to protect our astronauts from cosmic rays. Now, actually, on the surface of the moon or Mars, you can just go underground, but that involves a lot of digging, which involves a lot of heavy industrial machinery or a lot of shovels. Either way, that's a bunch of stuff that you need to haul to the moon or Mars in order to build those shelters.
Wow.
And then the transit itself, we need some method. And we have not cracked that.
Interesting. And these cosmic rays are the nuclei of helium, or is it a bunch of things?
Yeah, they're protons, they're helium nuclei, sometimes they're lithium nuclei. They're just subatomic particles that are going really fast.
And what is the thing that is so deadly about them? Is it the speed that they're moving, or is it the particle itself?
It is their energy. It is their speed. They have a ridiculous amount of energy.
And it comes from the sun?
The sun is responsible for some of these cosmic rays, but only a small fraction. Most of the cosmic rays come from outside the solar system. They come from exploding stars. They come from black holes tearing stars apart. They come from material falling into black holes. They come from stars crashing into each other. The most energetic events in the universe create absolute gobs of cosmic rays. And then you add them all together from all these sources, all these explosions, all these mergers, all these events, all these deaths throughout the entire universe. And you end up just everywhere soaked in cosmic rays.
Wow. And they're just moving so quickly. And I guess the only way to prevent it would be some type of atmospheric protection.
Yeah, so there are a bunch of proposals out there. One is to have your spacecraft generate a very strong magnetic field, strong enough to deflect the cosmic rays. That requires a lot of power, and it's not clear where you get the power from. Another is to surround your spacecraft with water. Yeah, just big old packages of water, and let the water do the absorbing. And then when the cosmic ray hits the outermost layer of the water, it creates a shower, but then there's even more water to absorb that shower of radiation so it doesn't reach the inner parts of the spacecraft. But that's heavy. And it takes up space, which increases launch costs. This is one of the many challenges we have as we're trying to design missions to Mars.
Right. This is a fundamental problem with long-term exposure
Yes.
to outer space and cosmic rays.
Yep.
Wow. That is interesting. And do you think that in our lifetime there will be some type of solution for this? I mean, this seems like such a massive problem.
Yeah, I think in our lifetime, there are people who are actively trying to design a legitimate mission to Mars. When it will happen, I don't know, because it depends on funding. It depends on technological breakthroughs that we do not have yet. It depends on a lot of engineering, a lot of mission planning. It's not impossible in our lifetimes, I believe, to send a crew on a mission to Mars. It will be incredibly expensive, perhaps the most expensive thing humanity has ever done, but it's not impossible.
And once we're on Mars, is there some type of protection from the cosmic rays from the atmosphere of Mars?
Unfortunately, the atmosphere of Mars is way too thin. It's about 1% that of the Earth. The only thing, your two choices are either to dig underground or to suck it up.
Wow. And do you know at what rate, if you're just getting a raw, shower of cosmic rays, at what rate you would develop cancer in your body? Is there some type of equation for that?
Yeah. For good or ill, we've studied radiation doses for a very long time. I don't know the numbers off the top of my head, but roughly speaking, a 2-year mission to Mars is several orders of magnitude greater than the maximum acceptable lifetime risk of radiation exposure.
And is there any possibility of growing agriculture on Mars? Obviously, the film The Martian, or the book The Martian, has this whole sort of theory that you can grow things and cultivate organic life.
Yeah, you can do it. I mean, we can grow plants in tubes of water. Because really all they need is water, sunlight, and some nutrients. And as long as they got that, plants are pretty happy. So you can use Martian dirt as a substrate. It is not the same thing as soil, because what we call soil on the Earth is actually a process from billions of years of evolution and microorganisms and macroscopic organisms constantly churning and moving and excreting and eating and changing the chemical composition of dirt into soil so that you can just plant a seed and the seed has everything it needs to grow. Mars doesn't have that, as far as we know. Also, Martian dust has a significant amount of something we call perchlorates, which is a form of rocket fuel, which, as you might imagine, is not what plants crave. It's not so great for plants. So you would have to rinse those perchlorates off, and then you just have a strata. You would have to inject nutrients. In the film The Martian, he used feces, human feces, to do it. There's sunlight on Mars. It's not as strong as on the Earth, but there's still sunlight. It's too cold on the surface of Mars, so you have to put this in a greenhouse. You have to get the plants carbon dioxide, more than what's available in the Martian atmosphere. But yeah, you could do it. It's just kind of hard.
You're right. It's theoretically possible.
Yeah, and people have built simulated Martian environments where they've sealed off a chamber, they've lowered the temperature, they pulled out most of the air, they reduced the ambient lighting to something like what you get on Mars, which is around 60% of what you get on the Earth, which is also equivalent to northern latitudes on the Earth in the middle of winter, roughly the same amount of sunlight.
Would the cosmic rays also affect non-human biological life?
Yeah.
Like it would cause breakdown to plants.
Cancer is
like
cancer. Yeah. Plants get cancer too. Do they? I said that and I sounded very confident when I said it.
But I guess if there's some type of like cell breakdown, right? Like
yeah, it just happens.
It'll create some type of decay.
Yeah. So that's a concern too. See, so which is even worse for the plants because they need access to sunlight unless you do the whole thing like a basement grow up.
Yeah. And then you're growing weed on the moon, like, or on Mars. Like, you don't need to grow weed.
Which might be the most valuable export they have. And this is what jumpstarts the next space revolution.
Yeah, it's just weed on Mars, Martian weed.
Martian weed, yeah.
That's so interesting. I guess that this cosmic ray thing seems like such a fundamental problem. It's just so crazy. Like aliens would also, if they're biological thing, like if they're living in the way we are.
Even if they're like machine intelligence and they're sending their robots out, cosmic rays are a problem for machines too. We have spacecraft that get glitched out because a cosmic ray, which is a charged particle, slams into one part of their sensitive semiconductors and electronic components and like fizzles a part out. Or we can see images from our space telescopes and the CCD arrays, the digital cameras on the back end. As time goes on, those sensors degrade from cosmic ray strikes.
Wow. That is fascinating. Now, back to the moon. Is it true that the moon came from the Earth?
As far as we understand, the leading theory of the formation of the moon is that it is a part of the Earth, or more accurately, a part of the Earth and another object that collided with us. Back in the early days of the solar system, when we were just a protoplanet, there were dozens of protoplanets, all competing for resources, crashing into each other, splintering off from each other. And we believe that an object about the size of Mars struck the young proto-Earth, temporarily vaporized the whole thing, formed this like giant cloud of goop. Most of the material settled back into the center, and that would eventually develop into the Earth, while a piece of it remained in orbit and it would coalesce to form the moon.
Interesting. Now, do all the planets in our solar system have moons?
No, Mercury does not have a moon and Venus does not have a moon. And Mars has 2 moons, but they're just captured asteroids. They barely count.
Oh, really?
Yeah. Phobos and Deimos are super small. They just were in the wrong place at the wrong time. They got captured by Mars's gravity.
Now, for it to be a moon, does it have to come from the planet itself, or is it just
No, the
the
definition
orbit
of
of the
moon
planet.
in astronomy is pretty loosey-goosey. Basically, if you're orbiting a planet, you get to be a moon. So that's why we have situations where like Saturn has, I don't know, 170 moons by now, because we're finding any old space rock that we can observe and say, yeah, it's orbiting Saturn, it's a moon.
That makes sense.
We're going to have to firm that up in a little bit.
Now, is it possible Earth could get another moon?
Occasionally, we do have temporary second moons, where just a random rock floating around the solar system ends up on a trajectory where it's temporarily captured by our orbit, loops around us for a bit or shares our orbit for a bit, and then wanders off. These can last anywhere from a couple years to a few thousand years. And yeah, so we have, like, I think we have a couple confirmed mini moons, second moons in orbit around the Earth right now.
Oh, interesting. Do those affect our tides?
Not at all. They're just too small and too far away.
Because the moon is obviously affecting our tide.
Yes, half our tides come from the moon and half come from the sun.
Oh, really?
Yeah, in order to make tides, you need a lot of gravity. And you can get a lot of gravity from either being really big or really close, preferably both. The moon is not so big. It's less than a tenth the mass of the Earth, but it's really, really close. The sun is very far away. It's 93 million miles away, but it's huge. And so those two combined affect our tides. Even Jupiter is too small to really make an appreciable difference here on our planet. And then if you have something like these mini moons or second moons, these things are like 100 miles across. They're nothing.
Does the moon do anything else to Earth other than the tides?
We suspect, it's a little hard to suss out from the mathematics, that the moon protects our seasons. Our seasons are due to our axial tilt. As the Earth goes around the sun, it traces out a circle, and the Earth is also spinning. And that axis of the spin is not perfectly perpendicular to the orbit. It's tilted by 23.5 degrees. And this tilt is what gives us the seasons. During half the year, the northern hemisphere is tilted towards the sun, and that gives us summer. And then 6 months later, the northern hemisphere is tilted away from the sun, and that gives us the winter. Planets in the solar system have all sorts of tilts. Some are nearly perfectly up and down. Some are upside down. Venus is actually upside down. Uranus actually points, its north pole actually points towards the sun. And for everything we can tell, these axes, these tilts change all the time from just random gravitational interactions or dynamics in the insides of the planets. Also, as far as we can tell, the tilt of the Earth has remained stable for billions of years, which does make us stand out relative to the other planets. And we think we have the moon to thank, because the moon acts as a counterweight to the spin of the Earth. And if our tilt were to change, the gravity of the moon pulls us back. So we believe that the moon stabilizes our axial tilt, which has stabilized our seasons for billions of years. So we have consistent summers and winters. If it weren't for the moon and our tilt were to start wandering, then life might have a much more difficult time.
Interesting.
Because the seasons would be much more unpredictable. You could have winters that would last 1,000 years, or summers that last for a century, or something in between. This would disrupt climate systems. This would disrupt weather patterns. And life would still find a way, because life is pretty clever, but it would have a much harder time for it.
Oh, that's so interesting. What's up, guys? We're going to take a break really quick because I have to tell you about an amazing new device called Fume. That's right, Fume. If you haven't heard of it, now you have. Fume is effectively flavored air. It's one of my favorite ways to de-stress. If you know me, you know I don't like to pick up bad habits, and Fume takes the bad out of the habit, okay? Instead of electronics, Fume is completely natural. Instead of vapor, Fume uses flavored air. And instead of harmful chemicals, Fume uses all natural, delicious flavors. I love the mint flavor. You take a deep breath, And the fume just feels amazing. It's a great way to de-stress. It makes you feel relaxed. And it's just a great way to even just like fidget while you're sitting in your chair. It just has like a cool little like bamboo knob. It's awesome. I love the fume. It just looks cool. It's super discreet. It goes in my pocket, through my backpack. I can have it at the airport. It's not a problem anywhere I go. And it just looks cool. It's fun to have. So let me just say this. Stopping something is difficult. It's hard to do. And that's why people put it off for a long time. But switching to fume is easy, enjoyable, and even fun. It really calms my anxiety and is a great way to de-stress. Fume has served over 100,000 customers and has thousands of success stories, and there's no reason that you can't be another one. Join Fume in accelerating humanity's breakup from destructive habits by picking up the Journey Pack. That's right. This is what I want you to do. You can go to tryfume, that's TRYFUM.com, and use the promo code GAGNON, GAGNON, the promo code GAGNON, and you will save 10% off when you get the Journey Pack. That's tryfume, tryfum.com, and use the promo code GAGNON, GAGNON, to save an additional 10% off your order. Kick the bad habits, take the bad out of the habit, take a deep breath of basically flavored air that'll make you feel amazing, take out the anxiety in your day, and make you feel more relaxed. Now let's get back to the show. Now, I've heard this idea that the moon is able to influence the liquid on Earth, right? It's able to move the tides. And if it's able to move the ocean, does the moon also affect the liquid within our bodies?
The moon affects the liquids of the oceans, yes. It also affects the continents. Our continents actually raise by a few centimeters with every tidal cycle. It's pulling, but rock is a lot harder to pull than water, and so it doesn't move as much, but it's the exact same physics. But it doesn't affect our internal bodies for two reasons. One, we're only like 6 feet long, at most.
Yeah, brag, Jesus.
Yeah. That's not a lot of water. That's not a lot of motion. In order to move the water on the ocean and actually affect a tide, you need a lot of water. And not just a depth of water, you need a breadth of water. Because what you need to do, if I'm the moon and I want to pull on an ocean, I need to take every little bit of water that I can influence and nudge everything just a tiny bit towards me. Because the gravitational pull, the tidal force is actually very, very small. But if you take that across the whole broad ocean and add up all these tiny effects, you get an overall raising of the sea level. We don't see tides in lakes, even the Great Lakes, because there isn't enough water to get together to make that motion work. And we're not going to see tides or gravitational influences in our own bodies because there simply isn't enough water to get the job done.
Oh, interesting. So it requires a large mass of water in order to see the detectable effects.
Exactly, because the effect is actually very, very small. But if you add up that small effect across an entire ocean, you get a raising of the tide.
Oh, that's so interesting. And so do these moons on other planets, like if they had water, would they affect the tides on those planets in the same way they affect ours?
Absolutely. And in fact, some of the tidal effects are so strong that you don't just get tides of water, you actually get tides of rock. We see this especially in the moons of Jupiter. The moons of Jupiter don't follow perfect circles.
This is Titan?
Titan is a moon of Saturn, but it's the exact same thing there too. So moons of Jupiter are Io, Europa, Ganymede, Callisto, and then a bunch of others that no one cares about. Io, the innermost moon of Jupiter, it doesn't orbit in a perfect circle. It orbits in an ellipse around Jupiter. So sometimes it's closer to Jupiter and sometimes it's further away. And the gravity of Jupiter is so strong because it's such a big planet and those moons are really close to that planet, that Jupiter creates tides on Io. It squeezes and stretches Io to the point that it heats up Io so much that it is volcanically active. There are more volcanoes on Io than there are on the Earth.
Wow.
It is the only other known volcanically active body in the solar system other than the Earth.
Do they resemble the volcanoes on Earth?
They're a lot broader and a lot shallower, but they're there. And there are streams of magma. It's like Darth Vader Hell Planet. It's right there in our solar system.
Wow.
And Io isn't alone. The next major moon of Jupiter is Europa. Europa has the exact same effects, the exact same tidal force, but because Europa is farther away from Jupiter, that tidal force is weaker. So it doesn't make the whole planet molten, only the interior. And this is why Europa is warm on the inside. This is what creates the liquid water oceans. It's not hot enough to melt the whole thing, only the inside. So the insides are molten from the tidal force and the outsides are frozen. And in between you have the liquid water.
Wow. And does does it affect a tide on Europa or Saturn on Titan? Are those liquids moving within a tidal stream?
Yes, they do. And this is one of our best pieces of evidence for the existence of liquid water oceans. The other piece of evidence we have is every once in a while, the liquid water ocean squirts out in the form of a geyser. And we can see it. We have literal pictures of these geyser plumes of water being squirted out of the surface of Europa. We call them cryovolcanoes, which is such a cool name. Volcanoes are what happens when you have a mountain made of solid rock and it squirts out liquid rock, which we call lava, and then cools and turns into solid rock. A cryovolcano is when you have a mountain made of ice and it squirts out liquid water that then freezes on the surface.
Wow.
And so this happens, we see it. The other big piece of evidence we have for the existence of these oceans are Europa, all these worlds are rotating, they're spinning as they're going around the planets. But the planets raise tides, which makes the moons wobble because it raises a different tide for the ocean than it does for the crust, than it does for the core. They get out of sync and they don't quite jive together. They weeble wobble. They don't fall down, but they do weeble wobble. And we can measure that. We can see the changes in the rotation as the moons orbit these planets. And we can put that together and say, well, the only way to get that kind of wobble is with a layer of liquid water.
Oh, wow. That is fascinating. Now, is it possible that the poles on Earth, I understand the poles are sort of shifting, that there's a shifting of the poles. I've read, and this is pure speculation, that the poles could potentially flip.
Yes.
And that could potentially be bad for life on Earth. Can you expand on that?
Yeah, so we have two poles. One is a geographic pole, which is the axis of rotation. This is what we typically call the North and South poles. If you were to imagine the Earth is spinning around a pole and you were to punch that pole through the Earth, that's where the pole would come in and out of our planet. We also have a magnetic pole. We have a giant magnetic field. It has a North Pole and a South Pole. The magnetic field comes out of the Earth in the south and then wraps around our planet and plunges in the north. I may have gotten that backwards, but either way, it's the same. These are the magnetic poles. These magnetic poles drift and have always drifted. The current magnetic North Pole is somewhere in northern Canada and is drifting westward. The reason our poles drift is because it's generated by complex motions of metals deep in our molten core. And because those motions are complex, they're not simple. It's a bit of a reductive statement, but you have very complex motions that can just change how the magnetic field appears because it's a very complex process and a very wishy-washy process that leads to the generation of the magnetic field. We have evidence that our magnetic field has changed direction in the past. Every few tens of thousands of years, our magnetic field tends to diminish, go away, and then reappear with the opposite direction. In terms of life on Earth, let's say our magnetic field were to go away tomorrow. Birds would have a really, really rough time because they use the magnetic field to drive their migration, to orient themselves. So they're going to be very confused, which will have a lot of ecological consequences. We would get more cosmic rays. We would get solar radiation. Thankfully, we have a very thick atmosphere that also does a great job of absorbing the brunt of those high energy, deadly cosmic rays and solar wind. If the magnetic field were to be gone for long enough, say 100 million years, we would be at risk of losing our atmosphere, just like Mars lost its atmosphere. We have a better job. We do a better job of holding on to our atmosphere because we're so much more massive. We have more gravity, so we can hold on to our atmosphere better, but we would start to lose it. So long term, that'd be kind of bad news for life on Earth. Short term, bad for birds. lowish to medium, baddish for everybody else.
Oh, really? So it would just be sort of an ecological issue. It wouldn't necessarily change the fabric of how, our Earth operates or the seasons or things like that.
No, we're good.
Oh, interesting. Do you find it significant that the sun and the moon, despite being so vastly different sizes and so different, it's so like the distance from Earth is so immense, and their difference in the distance of Earth is so immense, but yet when we look at them, they're roughly the same size?
Yeah, it's this wonderful and beautiful cosmic coincidence that the sun is about 400 times bigger than the moon, but it's about 400 times further away. And so they happen to have the almost exact same apparent size on our sky. This is how we get total solar eclipses, because if the moon were smaller, it wouldn't completely cover up the disk of the sun, and we would never see the corona around the sun during an eclipse, which for those listeners living in North America, the next opportunity is next April.
Oh, wow.
There's going to be a total solar eclipse passing over the continental United States. I believe it's April 8th, but don't quote me on the exact date. It will be coming up from Texas, coming through the Midwest, pass over the Eastern Great Lakes, and then exit through Maine. So if you're anywhere on that path, you will see a total solar eclipse. And we have the size of the moon to thank. If it was smaller, we wouldn't get totality. There'd always be a ring of sun around it. And if it was bigger, then it would cover up the corona, the pretty parts.
Mm-hmm.
This has not always been the case. Our moon used to be a lot closer to us, and the sun used to be a lot smaller than it is today. So we have two things. One is the changing distance to the moon. The moon, when it formed, was like a tenth its current distance, 10 times closer than it is today. But what happens is that the moon slowly inches away from the Earth. And the reason it does is the tides. So you put the moon, imagine putting the moon, freezing it in place, putting it over the Earth. It raises a tide. So there's a bulge of the ocean that rises trying to reach the moon. There's also a bulge on the opposite side, a tide on the opposite side that's trying to escape the moon. You get a tide. Now you press play. What happens? Well, the Earth is rotating. The Earth rotates. It carries those bulges with it. So now you have a situation, you press pause again. Now you have a situation where the tide that was raised by the moon is now a little bit in front of the moon. And this is an extra lump of gravity from the moon's perspective. It doesn't get to see this perfectly uniform spherical Earth. Now there's an extra lump over here. And that's a little gravitational tug that pulls on the moon and gives it just a little bit of extra energy. And in response, the moon goes further away. So slowly with time, the moon is drifting away, which means from our perspective, it's getting smaller and smaller. Simultaneously to that, the sun is getting bigger. With time, all stars, our sun included, get brighter and hotter and larger as they age. This is a very slow process, but around 100 million years ago, peak age of the dinosaur stuff, our sun was about 10% smaller. And 10%? Yes, 10% smaller and 10% dimmer than it is today. And it is slowly getting brighter, slowly getting hotter. So in a few 100 million years, total solar eclipses will be impossible. The moon will be too small and the sun will be too big. Also in 500 million years, our oceans are going to boil, but that's a different problem.
Right. That is so fascinating. And so I guess our recent ancestors, 1,000 years ago, it wouldn't be that different for them.
It wouldn't be that different, but what's amazing, this is such an interesting bit of astronomical history. We first realized, and I believe it was Edmund Halley who figured this out, that the moon is getting farther away from us. No one had thought about this or realized this, but he had access to ancient Babylonian records of total solar eclipses. And then he had access to more recent medieval and early modern period records of total solar eclipses. And he found that the total solar eclipses, the time between eclipses was getting a little bit longer over, say, 3,000, 4,000 years. And he did the math and he concluded that the moon is slowly getting further away from us. And then he was able to use Newton's newly discovered theory of universal gravity to figure out the interaction of the tides and what would cause that. And it matched the rate of progression of how the moon is getting further away from us matched his historical records that he had access to. And so that was the first time we were able to figure out that the moon is getting further away from us. And it's because we have astronomical records going back millennia.
Wow. That is so clever.
And smart guy.
Yeah. And I guess having astrological records from, 1,000 years ago would be helpful for probably a bunch of other, astrological conclusions, right?
Yeah. We've learned now that we have the benefit of hindsight, like people living 4,000 years ago, they didn't have 4,000 years worth of records. So they didn't notice some things. We were able to figure out that the stars are actually moving on the sky, that they're not so permanent. Based on early astronomical records and the record keeping that they had. We could compare it to more modern observations. We've figured out that there were stars in ancient people's skies that no longer are there. There are stars that were dim for them. They're now bright for us. There are stars that have changed their brightness over time because we have access to these records. Astronomy has this very, very deep recorded tradition. And so old that there are names of stars. Like there's one particular star, one of my favorite names for a star. It's in the constellation Corvus, the crow. The name of the star is Graz. We would write it G-R-A-Z, Graz. We don't know what that word means. We don't even know what language that word comes from. That language is extinct and has no written record. There are Persian astronomers from 1,000 years ago who are writing about this and writing like, yeah, we call this star Graz and we don't know why.
Wow.
It's from some language that we no longer have access to.
Oh, that's interesting.
And it persists to the present day.
Wow. That is so fascinating to me. And I guess just having all of these records for so long, every single culture throughout probably the genesis of human existence and the ability to look up and wonder what was above us, they've been taking record of those things.
Yeah. One of my favorite places is in New Mexico. Northwest New Mexico, there's a national park called Chaco Canyon. There were an indigenous people there. We don't know what they call themselves. They left no written language. We call them the Chaco. Presumably they called themselves
something else.
The Awesomeites or something. At the time, about 1,000 years ago, that area of New Mexico was much less arid than it is today. This was a settled culture. They had agriculture. They built temples. There are ruins that you can visit. And you can hike out to a cliff. And one of the things that the Chaco people enjoyed doing was petroglyphs and petrographs, drawings and carvings in the rock that the sun would then bake in to make them permanent. And you can go to one particular cliff overhang where you're looking up at a cliff and then there's a shelf. And you can look up at it and there's some petrographs there. And there's one in particular that's very strange. There's a handprint. It's a right hand. There's a crescent moon. And there's a star. Obviously, this meant something to those people who left no written language. We know when the Chaco lived there. It was roughly 1,000 years ago from various archaeological and radiocarbon dating. And it's reasonable to ask, was anything happening in the sky interesting about 1,000 years ago? Well, astronomy is a worldwide endeavor. We have records actually from 1,000 years ago from Chinese and Persian astronomers. There were also European astronomers, but 1,000 years ago, they were kind of busy killing each other. So not the greatest time to
They were busy.
record. They were busy.
Stuff to do.
Yeah, oh, here comes Alfred again. And get
genocide, whatever.
All right. Put down the telescope, guys. No, they didn't have telescopes. Okay. But both Chinese and Persian astronomers recorded the appearance of a new star in the sky that a few weeks later went away. And you can take that and say, okay, 1,000 years ago, the Chinese knew where it was. They told us, they wrote it down. And it was visible in the Chaco people's sky. And you can rewind the clock because you know the rough time frame. And the Chinese said this is when it happened, and but they didn't say exactly where. But you can rewind the clock to when the Chinese said this new star appeared, and you can orient yourself. You can plop yourself there at this location on the cliff. You can put your right hand up. You can wait. You can take astronomy software and wait for a crescent moon to appear at the right distance from your outstretched hand, and you can look. Like, is there anything there in that part of the sky? And there is. There's a nebula. What the Chacos saw was a supernova that was bright enough to be seen during the day. And the Chinese and the Persians had also seen it, and the Europeans were killing each other. Maybe they saw it, but they didn't bother writing it down. And so we have this people. We don't know how they spoke or what they talked about. We know very little about their faith, about their farming practices, about their culture, about their music. But we do know that they were astronomers, and we do know that they paid attention, and that one day they woke up and there was a bright star in their sky, in the daytime sky, that they had never seen before. And they found it momentous enough to record it. And here we are 1,000 years later, and we can hear them talking about it.
Wow. That is so fascinating. It just seems like every culture has a sort of like mystical romance with the stars, right? And there's astronomy, probably bordering on astrology in most cultures, even our culture today. I personally am not particularly a believer in contemporary astrology as we know it, your birthday, meaning whatever. I'm a skeptical person, I guess, maybe because I'm a Libra. But the idea that, the stars are affecting us, is there any credence to that idea that the alignment of the stars can change our physiology, change the way that we feel, change this idea that Mercury is in retrograde? Is there any scientific basis for these ideas?
Physically, no. Let's just get that right out of the gate. It's interesting you mentioned the difference between astronomy and astrology. For millennia, they were the same practice. The forerunners of modern science were astrologers. It wasn't until the early to mid 1800s that these started to diverge into distinct disciplines, with one being more scientifically credible than the other. But what we call the birth of modern science, the scientific revolution, was much more about astrology than it was about scientifically understanding the world around us. One of the most famous ones was Johannes Kepler. Kepler made massive contributions to our understanding of the universe. He was the first to discover that the planets move in ellipses around the sun. He was the first to discover a universal law that applied to the planetary motions. He realized that the time it takes for a planet to orbit around the sun is proportional to its distance around the sun.
He's the student of Tycho Brahe?
Exactly. Kepler was also an astrologer. And he believed most astrology was junk, but that his was better because he was better at it. And he was motivated in his scientific exploration of the universe to find astrological connections. He wanted to make astrology easier. He believed that the motions of the planets represented a form of divine music. He saw the patterns and harmonies in notes and music and believed that this was a reflection of creation itself, that this was closer to God, that this was so perfect and so orderly that it stood in contrast to our messy, sinful lives, that this was an echo of God's act of creation and God's perfection that remained in the universe today. And so he went looking to the planets to look for the music of the spheres, the music of the heavens. He would go on to say a bunch of very interesting things that do not appear in typical science textbooks today. Like, he looked at the motion of the Earth. And he saw that sometimes the Earth, when it's closest to the sun, goes faster than when it's farther from the sun. This is another thing he discovered in general about the motion of the planets. And he said, I can take the speed, the fastest the Earth is going, and I can take the slowest the Earth is going. And these are two numbers. I can make a ratio. I can put one number over the other, divide, what do I get? He found that this very nearly matches the same ratio between the notes fa and mi I'm not going to try to recreate it for you because I can't sing it all. But do, re, mi, fa, so. If you take fa and mi and take the ratio between those frequencies, it's very nearly the ratio between the fastest in Earth's orbit and the slowest that Earth moves in its orbit. So he said, of course, because this is Kepler, fa and mi. Of course, this is the ratio that dominates the Earth, where famine, fa, and misery, mi, hold sway on our Earth. So of course, it's fa and mi, because it's famine and misery. This is the condition of our world. Yeah, that was the general reaction of people like Galileo. They're like, great job, Johannes. Can you stop writing me letters? Eventually, we talk about the great scientific debate, was the Earth or the sun at the center of the universe? It was Kepler's work that really propelled the idea that we live in a solar system with the planets orbiting the sun. There was no scientific debate around this. There was no mathematical debate. What won the day? The reason people in the early 1600s started to believe in a heliocentric and sun-centered universe wasn't some victory of science over religion. It was because with Kepler's mathematics, horoscopes were easier to predict. The math was easier. It was simpler. You could do calculations faster and more accurately than the old models. That was it.
Literally horoscopes?
Horoscopes. Oh, and also, navigation, but that was like a minor side benefit. The major impetus, the major reason that motivated Kepler and why his mathematical model of a sun-centered universe with the planets moving in ellipses gained acceptance was it made horoscopes easier to calculate. That's it. That's the genesis of modern science.
That is fascinating.
It would take another couple hundred years for astrology and astronomy to separate.
Wow. And was it his intrigue in like horoscopes and astrology, or was it just like the culture at large just accepted it because they were like, oh yeah,
some of
horoscopes
our
work?
Astronomy has always been astrology up until the past 200 years. Some of the earliest writings ever. We're talking about Chinese characters written onto tortoise shells from thousands of years ago. One of these earliest writings, if not the earliest Chinese writing we have, is a story of two astronomers. They were court astronomers for the emperor at the time, who had failed to predict an upcoming solar eclipse. They were promptly beheaded because apparently they were out getting drunk and partying instead of doing their job. So back then, the stakes were a little bit higher for astronomers.
But still nothing changes, though.
What happens in the observatory stays in the observatory. Yeah. Astronomy has always been astrology, and it's only recently that it has split, where astrology is now disregarded as a pseudoscience. Mm-hmm. The positions of the stars have no physical influence on your daily life, unless you believe that they do, in which case you start changing your own life. Like, you're going to have a great day today. If someone told you, and with from a position of wisdom and trust and respect, like your therapist, like I see a therapist and therapist saying, you know what, this week will be better. You're working really hard. Dang it, I'm going to work to make this week better.
Right. Yeah.
And that's useful.
Placebos are effective.
It's not just placebos, because it's, people seek comfort in a chaotic, messy, unpredictable world. Mm-hmm. I am one of those people. I go to my doctor. What is this ache I'm having? I want some comfort. I want some treatment. I don't want to worry about if I'm going to start falling apart tomorrow. I go to my therapist and I talk about, the troubles I'm having, the worries I'm having, and he navigates me through those thoughts and feelings and equips me with some tools to navigate everyday life. Astrology obviously plays a role in many people's lives. I believe it's from an incorrect basis, but also I can't begrudge someone for wanting to get control of their lives and make some sense of this weird universe that we find ourselves in. Mm-hmm. So yeah, if someone asked me, do I believe in astrology? No. But is astrology a force in people's lives? The answer is yes. And there's a reason for it. And I'm not going to judge anyone for wanting to seek comfort in this world.
Interesting. Yeah. And I guess if you do believe it, could it manifest a way in your life that would give you more order or give you more of an explanation to the chaos that exists around us?
Yeah. Life is hard.
Yeah.
And if you want to, if you have your way of making life a little bit less hard for yourself and it's not harming anyone else, do it.
Oh, that's so interesting.
Who cares?
This is a silly thing. I didn't even realize, but like the constellations that we see, I assumed that everyone on the Earth also saw these constellations. That the idea that the Big Dipper was,
Always the Big Dipper.
everyone sees it.
But the Big Dipper isn't even the Big Dipper. It's just a part of Ursa Major, which even I have a hard time outlining Ursa Major, the actual constellation. That's just the tail of the bear. It's actually part of a much, but we're so used to just seeing the Big Dipper. Also, it's the brightest part of the constellation. We have a hard time seeing the bear. We just see, it's a ladle. I mean, who uses ladle?
Yeah.
There are constellations like Canis Minor, the small dog, is 2 stars.
That's how I feel. I look at
like,
these.
that's cheating. That's cheating.
Orion's belt. I'm like, that's just a bunch of stars. Like, it doesn't look like anything.
Yeah.
That's how I feel about most constellations.
No, it's constellations. Well, there's 2 issues here. One is we're losing access to the night sky.
Right.
With light pollution. We do not have the same sky that our ancestors did. And most people don't even see a small fraction of the stars that are truly out there. On a clear, dark night, away from light pollution, you can see around 3,000 stars. Most people see no more than a few hundred and go their entire lives seeing no more than a few hundred. When you see a clear, dark sky, and I've had the privilege a few times in my life of seeing the sky as our ancestors saw it. I've been to the Atacama Desert of northern Chile, which is a dark sky preserve. I've been in the middle of the ocean with the lights out on a sailing ship and been able to see the stars. There is something powerful and transformative about seeing the sky. And of course you're transported there. Of course you're overwhelmed by it. On one hand, it seems distant and alien and impossible to reach. And on the other hand, it seems like right there. It's our sky. It's right there. It's a part of us. Cultures around the world have created their stories. It's the playground for an imagination. You can take any grouping of stars and use your imagination. You know, if you were ever a kid and looked at clouds and say, that's an alligator. Well, no, I don't see an alligator. I see something else. You do that with the stars and you start telling stories. They serve as backdrops. They're the first movies that we had where you could tell a story and look at something at the same time. And a lot of cultures share at least some of the constellations, like the constellation Orion. Seeing it as a person is shared among many, many different cultures. But then other cultures come up with completely different constellations. And it's so beautiful to think of not the cultures that exist today, but the cultures that have existed throughout human history, both written and unwritten. We've all shared the sky. We all have that in common. We've all looked up and wondered, what are these tiny points of light that dazzle us every single night? And we've all used it. Every single human culture has told stories and formed constellations. That's something we all have in common. And I see astronomy, modern astronomy, we don't worry so much about constellations, but we're telling stories about the sky. Except our stories are about merging black holes and stars exploding and the emergence of life on exoplanets. Those are the stories we tell, but they're still stories. Where modern astronomy is a part of that myth-making tradition that we've had access to since we've been humans.
Do you think there is a psychological effect, a negative psychological effect to society as we're getting less connected to the stars on an everyday basis?
Absolutely. This is a natural resource. It's like asking, is there a negative effect to losing all the wetlands or coral reefs? This is a part of our natural world. It is something that humans have enjoyed access to for tens of thousands of years, if not hundreds of thousands. I don't know at what stage in our evolution we began asking questions about the night sky, but ever since that time, we have. And it's not just a question of urbanization and light pollution. And the more and more people that live in cities, the fewer and fewer people have access to the stars. Light pollution, especially from constellations of satellites, because they reflect and scatter sunlight everywhere in their orbit, it's raising the overall brightness of the sky. So even the darkest places on Earth are not as dark as they were 100 years ago.
Wow.
The stars that you could see with the unaided eye 100 years ago, there are stars that are impossible to see now because of the global levels of light pollution. And it's only going to get worse. There are organizations like the International Dark Sky Association that try to balance the needs and desires of modern society. We want our cars. We want our streetlights. We want lights in our home. We want to be safe. We want to illuminate the night. But surely there's a way to do this while still balancing and respecting this natural resource that a lot of people don't respect because they spent their whole lives not seeing it for themselves. And when you see a true night sky with no light pollution on the horizon, I live in Connecticut, I get light pollution from New York and Boston and Hartford. It's not the same sky that I grew up with. I grew up in the middle of nowhere in Ohio. It's not the same sky I had growing up. Now I have to travel to get access to those skies.
Right.
And the more that people have to travel to access those kinds of skies, the less they care about it. And I believe more people should have access to it. More people should experience it. There is something soulfully moving about a dark sky that you are exposed to. You do get a sense of cosmic insignificance. You are transported to a place of wonder and curiosity and expansive inquisitiveness. Humility, and also specialness. You look at all those thousands of stars and we know for a fact that no one's looking back at us from any of those thousands of stars. And so you look around at the people you share your life with and you share this world with, and you realize this is it. I wish more people could see the night sky.
That's very interesting. Yeah, I don't know if people really wonder or acknowledge the psychological effects of being disconnected from this thing that all of our ancestors, for the vast amount of human history, have been deeply connected to. Whether it's through navigation, whether it's through astrology, whatever that relationship is, it is intrinsic to the human experience.
It is. It is a part of our experience of the natural world and our connection to the natural world.
Mm-hmm. And we just don't really interact with it in any significant way.
Not anymore.
Yeah.
Like if you live in Manhattan, your best view of the nighttime sky is the planetarium, the Hayden Planetarium at AMH.
Yeah.
An artificial reconstruction of the night sky. And it's not the same.
It isn't. No, I wonder if even on like a spiritual level or something, like there's a zhuzh about it that you see it and it truly moves you. All of those things that you mentioned, I've had the experience of seeing sort of a pure night sky. And it is awe-inspiring. It's like the colors are so vibrant. It's not just black and light. It's alive. Yeah, it is truly like an organism in its own right.
And if you can see the Milky Way, snaking through the sky.
Oh my goodness.
I don't know. I still get blown away looking through a backyard telescope at the moon. I show people, I'll bring a telescope somewhere and I'll just point it at the moon and say, hey, look at this. And they look and they see the shadows in the craters. And they're like, oh my God. Yeah.
Yeah, it's right there.
It's right there. You look at Saturn, you can see the rings of Saturn. Or you look at Venus and you see that it's actually a crescent. It has phases just like the moon does. You're like, wait, what?
Yeah.
I see, here's Jupiter. You see those little dots? Those are the moons. That's Europa. There's liquid water right there in that point of light.
And we don't even know.
What?
I didn't even know there was liquid water in our solar system. I thought it was just the Earth.
Oh, yeah. This is crazy. This is only the past couple decades we've made this revelation.
Now, what are your thoughts as far as lost technology goes for humanity when it comes to interacting with the stars, right? Like, I kind of have a hard time believing that Galileo was the first guy to be like, hey guys, I got a telescope and I don't think the Earth is flat, and like, or was it Copernicus? Regardless, this idea of a heliocentric solar system, all these things are relatively recent in human history. And then we see the Egyptians are building, these massive pyramids that have all these astrological features that are connected to it, and cultures in China and Mexico that are all building these features that are interacting with the stars in some type of significant way. I just kind of doubt that it's like one dude in Europe. He seems like the most recent guy to figure it out. What are your thoughts?
Yeah. This is a good line of questioning, because obviously humanity has had an interest in an interaction, that's a great word for it, with the night sky for ages. Look at Stonehenge. Thousands of years old, obviously astronomical. It's not a coincidence that during the equinox, the light falls through in a very specific way. It's not an accident. You go to a random tomb in Egypt. It's not an accident that during, like, say, a solstice, the light pierces through a tiny keyhole and illuminates a feature of the temple. That's not an accident. In Australia, there are megalithic structures, like stone structures, that it's not an accident. They're lined up. You go to Mayan temples, and it's not an accident that they're aligned with Venus on particular days of the year. These are not accidents. We have paid attention to the night sky for a very long time. The night sky is useful. It's a natural clock. When is spring coming? I don't know. Oh, it turns out that this star rises at a very particular position on the sky every time spring is about to come. And that means in the next couple of weeks, the rains are coming. So we better start planting. Not a coincidence. People are smart. People have been smart for millennia. We're just as smart. They were just as smart 10,000 years ago as they are today. They just don't have Wikipedia. Mm-hmm. They paid attention. They were smart. They were clever. They found these patterns in the night sky. That is something that is absolutely magical and powerful about the night sky, and why we always associated it with divinity, because everything on Earth is super chaotic and messy and unpredictable, and yet the sun rises in the east every single morning without fail. And it has since the dawn of human memory. The moon comes around every month. The same stars come around every single year. It's the only thing you can count on in this entire universe. Yeah, the river floods every year, except when it doesn't. Yeah, our crops grow every year, except when, bugs eat them. But man, the planets are right there.
Yeah.
The stars are right there. The sun is right there. Every single
Even
time.
Agriculture is a relatively recent invention in human existence,
Absolutely.
right? So even that, like, their ancestors didn't even have that type of, faux consistency.
Exactly. The stars are the only things we can count on. Or at least our ancestors. And of course, humans are bright and creative, imaginative, curious, and have been ever since there have been humans, because that's part of what makes us human. We've known that the Earth is round for thousands of years. There were clever experiments going on over 2,000 years ago that measured the circumference of the Earth to within 10% of the modern known value. Mm-hmm. Absolutely clever people. Among those clever people were a kind of people who like to ask questions, especially difficult questions. We call them the philosophers. Every culture has some version of philosopher. Philosophers like to ask very cool questions, like, what is the universe made of? And what is ethical? Fun questions that have no easy answers. I am sure, both written and unwritten, that there are examples of people who guess that the sun is at the center of the universe. There was, however, something special that happened in Europe about 400 years ago. there was a confluence of philosophical thinking that led slowly, painstakingly, and in fits and starts to an emphasis on empirical validation of you can't just have a good idea and argue that good idea and have it sound good. Can you collect some recording, some observation that we can all agree on that settles this question once and for all? That is the birth of what we call modern science. There was something special about Galileo. He was certainly not the first person to look up in the night sky, but he was the first person to take a piece of glass and carve it just the right way with enough precision that it could magnify distant objects and still be clear and sharp and visible. And he was the first person to take that instrument that had been around for over a decade, but refine it to such a degree that he could look out at the night sky and see craters on the moon, dots of light orbiting Jupiter, the crescent of Venus, sunspots, that he could reveal the universe in a way that no one else has. There is no one else before Galileo had done that. No one else had the technology to do it. No one else had developed curved pieces of glass with just the right properties and just the right level of finesse and fidelity to make those kinds of observations happen. Something special did happen in Western Europe about 400 years ago that we now call the scientific revolution. Every thought that we have about the universe has its philosophical precedents, and probably even deeper into the past. I'm sure our ancestors 20,000 years ago, as they were hunting woolly mammoths, were sitting around the campfire telling stories to each other and wondering about the nature of what they saw in this world. And I'm sure someone at some point guessed the right answer, or what we consider currently to be the right answer. They may not have used words like hydrogen and fusion and light year, but they probably got the sentiment right. So I wonder if those dots of light are just like the sun, but really far away. That's a cool thought, Ugnaught. You know, past the woolly mammoth steak. Unfortunately, we don't have access to their thoughts unless they wrote them down. And that's only a relatively recent thing. Greek philosophers, they did write lots of things down. We do have access to their thoughts, and they got some ideas right. They also got some things wrong, but we can't fault them for it because, you know, they're just as lost and confused in this universe as we are. But something special did happen a few hundred years ago in Europe that appears to be singular in human history. The scientific enterprise, the scientific exploration of the universe is a relatively new thing. It is one of the newest ways that humans have used to make sense of the universe. Faith and philosophy and mythology, even astrology, have been with us for millennia. Science is not. And of course, the seeds of science, the precedents of science, the threads of science stretch back millennia, but not in this particular combination. You did need millennia of thought and refinement of thought and technology and refinement of technology before you can get something like modern science.
Now, this idea of, you know, like the two major misnomers it seems like people, you know, prior to the scientific revolution in Europe had was that the earth was flat. This is an idea that people have touted. I've also heard that no one actually really thought that for most of human history, people knew that it was round, and that this idea of a flat earther was like a pejorative that people would use towards, I guess, like non-scientific people. Have you heard this theory before?
Yeah. So at the time of the scientific revolution, about 400 years ago, roughly, to be fair, the vast majority of people were subsistent farmers who probably didn't give much thought to anything except trying not to starve. And that's been true of the vast majority of people throughout human history. We do live in a very special time where most people are not starving. And this is a new thing. So there wasn't a lot of brain power left to ask questions about, you know, the nature of the cosmos. But people who did think about this and write about it and talk about it had known that the earth was round, and we've known it was round for thousands of years. most cultures around the world, at least early on, did believe that the Earth was flat. I'm actually don't know if, say, Chinese thinkers around 400 years ago or South Asian thinkers, what their conceptions of the cosmos was. There's also really fun, interesting cultural discussions to be had. Like, if you don't consider the shape of the Earth to be an important question, then you're not going to ask that question, let alone answer it. And so you're not going to have a strong opinion on it because you're thinking about other things. But certainly in Europe, there had been a tradition of thinking about the shape of the Earth and what that means. And this was an important question for at least some people who thought about it. And they had answered it conclusively. The Earth was round, and everyone knew it was round. Christopher Columbus got a lot of flack. He was rejected from a lot of his initial early proposals to sail across the Atlantic because he was going on either deliberately falsified information or just plain wrong information that said the Earth was a lot smaller than we had previously believed, and that a couple months voyage would get him to the shores of Asia, which he believed he did, which is why we call it the West Indies, the western part of the Indian continent. Like that is why we call it that, because he thought he was in Asia. He was dead wrong. And he was laughed at by a lot of very smart people, not because they thought the Earth was flat, but because they knew it was a lot bigger than good old Christopher Columbus said it was. So that was simply a debate that was put to rest like 2,500 years ago.
Interesting. And then the other debate, I guess, is geocentrism versus heliocentrism.
Yes.
That the church held on for a long time that the Earth was the center of our solar system, that all the planets orbited around the Earth as God's divine creation. And then that was found to be not the case. The early appearance of science around 400 years ago, and what we call the scientific revolution, in the relationship between those early scientific thinkers and the Catholic Church, is much messier and much more nuanced and much more tangled than anyone would care to admit. For example, we can't import our modern scientific sensibilities. Like, I see the world a certain way as a scientist. I also see it other ways as a non-scientist. But I focus on like empirical verification, rational methods, strongly verified mathematical arguments, et cetera. So, the foundations of modern science. We didn't have that 400 years ago because we hadn't invented it yet. So you have people like Copernicus, who initially propose in mid to late 1500s that maybe the sun is at the center of the universe. The arguments that Copernicus put forth, some of them look scientific. Like, hey, if the sun is at the center, then it makes orbits easier to calculate, or like it's a better model. Some of them look very, very foreign to modern eyes. Some arguments like, so you know how Jesus Christ is the Son of God, and he is the light of the world and the center of our faith, right? We've all established that. Well, the sun is also the light of the world and should therefore be at the center of the universe. Right.
Get it? Sun.
This
Doesn't
is a little
this
bit
make
of
sense?
a famine misery type connection.
Yeah,
here.
exactly. At the time, Copernicus could list arguments that seem sensical and nonsensical to us, but at the time, because we didn't have this strict separation of scientific investigation versus theology versus mathematics, he could list all of them, and all of them were taken seriously. His contemporaries are like, oh man, good point, Copernicus. When Copernicus released his book on his deathbed, the book was published, was distributed, was thought about and debated, but at a very, very low level, at a very like elite educated level in early modern Europe. We see people responding to it, distributing copies and going like, interesting thought. And then you get to characters like Tycho Brahe, Johannes Kepler, Galileo, who are like the next generation. Galileo finds himself in hot water. He argues that the sun is at the center of the universe. And this was a topic. Like, what is at the center of the universe? Is it the Earth? Is it the sun? At the time, there was no good evidence either way. Copernicus's model was a little bit simpler than the Earth-centered model in its ability to explain the motions of planets, but not that much simpler. Because Copernicus still had the planets moving in circles. It would take Kepler to figure out that they're ellipses. But before that, if you assume the planets are moving in circles, you're not doing much better mathematically. And then there are extra arguments. If you're like, okay, Copernicus, if the sun is at the center and we're moving, well, how does the Earth move? Why don't we feel it? Where's the wind? Why don't we slow down? You're saying this has happened forever? How can something move forever? These are valid arguments. Now we have answers to those arguments. It's all gravity and space is empty. But they didn't have that evidence 400 years ago. So it's a valid debate. And the church is the one organization that is financing these debates. Or one of the organizations. They're financing scholars. They're bankrolling Galileo. Galileo gets in hot water because he insists that the sun is at the center of the universe. But Galileo, even though Kepler is writing him like fanboy letters saying, I think they're ellipses, Galileo's like, please stop talking to me. You're such a weirdo. He ignores it and he thinks the planets move in circles. And then they grill him on this. They're like, Galileo, you say it's circles, but like that doesn't work. It doesn't explain the observations much better. So what's the deal? And Galileo's like, shut up, they're moving circles. And then Galileo takes it one step further. He's commissioned by the Pope Urban II, if I got the name right, to write a book. He said, okay, Galileo, we want to sponsor this. Could you write a book expressing both views? One view for the sun-centered heliocentric universe, one view against. I, Pope, believe that the sun is at the center, but I want to do something fair and balanced. And Galileo says, sure. Writes a book where the character who represents these the geocentric universe, the Earth-centered universe, aka the Pope, is basically named Moron. As a moron says the Earth is at the center, and then like Smarty Pants says, you idiot. This gets him in hot water.
Yeah.
At the time, this is before Sinead O'Connor, you don't tear up pictures of the Pope.
Right.
And even then, like all the way up until 1992, this was a tough thing to do.
Yeah.
So of course the church got mad. And should they have put him under house arrest? Of course not. It's heinous. It's horrible. Was it about a rejection of the sun-centered universe idea? Kind of, sort of, yes. But also you have to broaden your picture, because it was about much more than that. And these weren't scientists as we currently consider them scientists. They were proto-scientists. These were people arguing from a variety of opinions and perspectives, theological, philosophical, mathematical, and observational and empirical. And to just reduce it to the church was evil and science was trying to break free does a disservice both to the church and to science. It simply wasn't like that. Like I said earlier, we eventually grew to accept the sun-centered universe idea, not through any great scientific argument, not through any great empirical observation, not through any great proof, but because horoscopes were easier to calculate. Eventually all that would come. We would understand why we don't feel the wind of the Earth orbiting the sun. We would understand why the Earth doesn't slow down. We would understand why circular orbits don't make sense. We would come to understand that, but that would actually take centuries. And so to take knowledge that was acquired literally hundreds of years later and apply it to the early days of the scientific revolution, it does a gross disservice to the people who were advocating for these positions, who were all very brilliant people, and the people who were advocating against those ideas, who were also brilliant people. They just happened to be wrong. But you can't fault them for being wrong.
Interesting. That's a cool delineation. This idea that there is an archaic church that is stupid and backwards, and genius scientists that are figuring everything out, that are getting persecuted for their genius, is a oversimplified and
highly oversimplified.
Yeah, bordering on just fallacious.
And not that the church, including the modern church and the medieval church, did not commit innumerable sins, and they shouldn't have been burning people alive, and they shouldn't have been placing people under house arrest, and they should have probably moved faster with the arguments that were being offered. I'm not trying to excuse any of that, but also they were burning people alive and putting people under house arrest for a whole bunch of other reasons too.
Right. Now, this is a personal thing, but my parents are devout Catholics. I was raised Catholic, and they are like bordering on geocentrist in the current day. They are toying with this idea that the Earth as God's divine creation is the center of the universe. My mother has floated a few different ideas out that apparently NASA uses geocentric modeling when it comes to some of their calculations, and that there's a movement to basically undermine the divinity of God's creation. So I'm curious, is there a simple, compelling argument that I could explain to them about why the universe is heliocentric? Also, just to clarify, is it the universe or is it our solar system that is heliocentric?
So yeah, I was a little fuzzy on this language. 400 years ago, the debate was what is at the center of the universe, because all we knew was the solar system. And then we assumed that the firmament was this sphere of fixed stars surrounding us. Nowadays, we only talk about the solar system.
Right.
And yes, it is true that NASA, in many calculations, like if I'm launching a satellite into orbit around the Earth, I don't care about the sun. I care about the satellite and the Earth. So of course I'm going to use a coordinate system that places the Earth at the center of the quote unquote universe, because in my calculations, all I care about is the Earth and the satellite. That is my entire universe. It's interesting you say you were raised Catholic. I was raised Catholic too. In fact, my dad was a former Catholic priest. He was a priest before he became my dad. But he actually left the priesthood because he fell in love with my mom and wanted to do it right. And my uncle is just retired last year after serving for nearly 50 years as a Catholic priest. So he's still technically a priest, but just like a one who wears sweatpants. Oh,
how interesting. So were you raised very Catholic?
Absolutely.
So your father, despite leaving, his vocational work, was still a devout
very,
Catholic.
very faithful to the church to his dying day. And I was raised full on Catholic.
Oh, how interesting.
I fell asleep in the pews every Sunday.
Sure.
But that gets in there,
though. That gets in there.
It gets in there. Didn't work out so well. Not Catholic anymore. But I even went to Catholic school, nuns, the whole deal. And
that's crazy, dude. You got a father and a daddy. That's wild, dude. That is fascinating.
Yes. And one, there are no arguments that are going to dissuade your parents.
Sure.
I have encountered many people in my life who believe things differently than I do. And there's either room for interesting, fruitful discussion where you both learn, or there isn't. And if there isn't, just talk about other things.
Right.
But if you wanted to bring up an interesting point, one would be to place the divine creation of the Earth in its correct context, which, yes, the medieval Catholic Church did believe that the Earth is at the center of the universe. That was not a good thing. We were not the pinnacle of creation. We were not the focus. In medieval Catholic cosmology, the Earth was at the center of the universe, and we were surrounded by a series of crystal spheres. Each one of these spheres carried with it a heavenly body, and the spheres glided effortlessly against each other. So there's one for the moon, one for the sun, one for each of the planets, and then the outermost one carried the stars. Beyond that, outside the realm of these crystal spheres, was heaven. This is where God, Jesus, Holy Spirit, angels, etc. lived. Where was the earth? As far away from heaven as you could possibly be in the entire universe. Why? Because of original sin. We were meant to be the pinnacle of creation, but we screwed it up. And our sinful ways placed us in the center, not the center of a mountain, but the center of a garbage pile. The earth was chaotic and sinful and gone astray because of our original sin, and that placed us far from heaven, far from divine grace. That was our place in the universe. It was not a place you wanted to be. That is why Kepler looked to the stars and the motions of the planets for inspiration and guidance, because he believed that because they were literally closer to heaven, that they had a stronger connection to the voice of God. And by analyzing and studying the motions of the planets, you could glean some of God's divine perfection from that and use that to improve your life through astrology. Even Galileo believed this. Yeah, Earth is at the center. We're the messy, disgusting, distant parts of the universe. It's not always good to be at the center. That is what the Catholic Church believed. And that it was our goal as humans to leave this earth. Because if Earth is at the center and it's so great, why would our souls want to leave? No, they want to get out of here and they want to go to heaven. And what's in the center of the earth? The absolute center of creation? Hell itself.
Interesting. So even this idea that a heliocentric model could actually be more compatible with religious dogma and our understanding of God's creation of the universe. And it could fit more harmoniously with the idea that we are special and not insignificant. I guess there's this idea that if we are operating under this heliocentric idea, that the earth is irrelevant, that we're just a ball floating in chaos, and there's just all of these, we're just insignificant in God's creation, but perhaps it makes us more significant that we're not as far away from heaven as possible.
Yeah, the heliocentric model, the sun-centered universe, and at the time it was the universe, completely destroys this entire picture, especially with Kepler's ellipses. It's one thing to have crystal spheres gliding effortlessly against each other, but crystal ellipsoids don't exactly glide effortlessly against each other. And then if there are no crystal spheres, then there's no beyond the crystal spheres, which means where exactly is heaven? You told me it was over there just past the stars. In fact, that's why the stars are bright, because they're like little pinholes that allow us to view heaven, as some people thought. So where is heaven? And then where exactly is hell? So you need not just a revolution in an understanding of physical cosmology, you also need a revolution in mythological and theological cosmology. And at the time they were intertwined, and in fact through all of human history they were always intertwined. There was just the universe, which contained some physical parts, some metaphysical parts, some aspects of the natural world were divine and some were not. Beginning 400 years ago with the scientific revolution, we started to really make some great strides in understanding the physical world. But then how do you make a mythological world, a theological world that is also compatible with that? That is not an easy question to answer. And that's a question that still confronts us today. When we as scientists say, the universe is 13.77 billion years old, plus or minus 100 million years. And at that time, 13.77 billion years ago, our entire observable universe was the size of a peach and had a temperature of over a quadrillion degrees. Like, wow, that's really cool. What do you call it? I say, I call it the Big Bang. They say, okay, where did that come from? And I say, I don't know. Here we have a physical cosmology that must be reckoned with, if you're a person of faith, with a metaphysical cosmology and even a philosophical cosmology. Like, okay, I can tell you with the conditions of the early universe, I have no idea as a physicist where the universe came from. I have no idea what created it, if that word even makes sense, because we're kind of on the limits of human comprehension here. And a philosopher can say, well, okay, you can explain the Big Bang, but can you explain why there was a Big Bang in the first place?
Right.
Like, say, well, it's a set of physical laws. Okay, why are there physical laws? That's a very valid question. It's a deeply valid question that intersects physics and physical cosmology, which is my discipline, my specialty. And I do believe there has been a trend over the past 1 to 150 years to put science in a little box over here and have scientists stick to their lane and have them try to understand the workings of the physical universe, which is super fun. And then have theologians stick to their lane and have mathematicians stick to their lane and have philosophers stick to their lane. This used to be all mixed up. You went to school at one of the great universities 1,000 years ago. You learned all of it. And I do believe if you as a human want to have an understanding of the universe, you must answer questions along all these lines. What was the state of the early universe? That's a physics question. Why does the universe exist or not? That's a philosophical question. There are religious questions. There are mathematical questions, and every single human, answers these questions to some degree. And I think it's a mistake for modern science to close itself off from engagement with religion, with theologians, with philosophers, with musicians, with artists. I think we're missing something as scientists when we do that too much. And the arguments of Copernicus and Galileo and Kepler seem foreign and alien to us because we do science in a different way now. But they were onto something, and they were making valid arguments about a universe that they barely understood. Mm-hmm. We still barely understand the universe, just slightly less barely than we did before. But there's still so many wonderful things to learn. And I do believe that science can only take us so far. There are only so many things we can learn through scientific inquiry. And the rest we have to talk about.
What's up, guys? We're going to take a break really quick because you need an attorney. That's right. Maybe you were in a car accident. Maybe you slipped, leaving your apartment, leaving your house. The sidewalk was all wet. Who knows? Maybe you need an attorney. And if you do, you got to check out Morgan & Morgan. That's who I would probably call. If something happened to me, if I was riding my bike and I crashed, or someone crashed into me, the worst thing about an accident is barely even the accident, right? I'll have back pain. You'll have neck pain. Who knows? The worst part is trying to find an attorney. It's exhausting. You go online, you search all these websites, you're going through Google, you're like, who is this guy? If you're young like me, you've never got an attorney before. It's a really, really challenging thing to do, and it can be super confusing. And that's why you could go to Morgan & Morgan. Morgan & Morgan is America's largest personal injury law firm. They have over 100 offices nationwide and more than 800 attorneys. That's right. They have recovered over $15 billion for their clients. It's so simple. 8 clicks or less. You go to Morgan & Morgan, you can submit a claim. And now here's what's amazing. They don't charge you a single penny unless they win your case. You got nothing to lose. So if you're ever injured, you could go to forthepeople.com/gagnon. That's correct. For the people, FORthepeople.com/gagnon. Or dial #law, that's #529 from your cell phone. I'm telling you, Morgan & Morgan, these are great guys. Dan Morgan is an absolute legend. If you don't know Dan Morgan, he's an attorney, but he's even more than that, right? He's a writer. He's a rapper, one of the greatest rappers of our generation, okay? So if you're ever injured, you could check out Morgan & Morgan. That's forthepeople.com, forthepeople.com/Gagnon, Gagnon, or dial #law. That's pound 529 from your cell phone. That's forthepeople.com/Gagnon, or dial #law, pound 529 from your cell phone. If you're injured, you could check them out. And by checking them out, you help support the show by supporting the sponsors that sponsor the show. And that helps us get amazing things like this brand new studio that we're going to be recording all of our episodes out of. So thank you to all the sponsors. Thank you to Morgan & Morgan for supporting us and supporting the dream of creating the greatest podcast in the world. Now, let's get back to the show. There seems to be a very obvious intersectionality with all of these questions, right? Like the idea that most physicists can kind of come to an agreement about what the universe was like seconds after the Big Bang.
Oh, yeah.
If we're subscribing to that theory, you know, if there even was a beginning, right? So to that point of, does the question even make sense? But hypothetically, let's say we're following this Big Bang idea. Most physicists can be like, yeah, this is generally what things were like, you know, an hour after the Big Bang.
And we have gobs of evidence that tell us this is the right story. So like,
but 1 hour before.
Yeah. If the word before even makes sense.
Yeah. It is
I don't know.
It is a complete mystery.
And these kinds of questions, these like limits of physical understanding, aren't just contained to cosmology and the Big Bang. I can ask other questions. Like, I know this sounds so inane. Like, what is love?
Baby, don't hurt me.
Well, there are aspects of love, of the sensation of love, and the manifestation of love that I can answer as a scientist. I can talk about neurochemistry. I can talk about pair bonding. And there's certainly, and those are very real things.
Anthropology, our development of our species.
Exactly. But that's not the whole story. That's not it. That's not the totality of love. There's a part of love that an artist can express, a musician. There's a movie that can depict it, that makes you feel a certain way, that gives you a new understanding of what love is and means to you as a person. And that's not the totality of love. I can ask a slightly less inane question, like, what is time? Well, gee, as a scientist, as a physicist, I can tell you a lot about the nature of time. We talked about time dilation. I could talk about the arrow of time. I can talk about time all day long. In fact, I have before.
Yeah.
But that's not the totality of our experience of time. Philosophers have a lot to say about the nature of time. Theologians have a lot to say about the nature of time. Musicians and dancers have a lot to say about the nature of time. And that's none of these areas of inquiry, as I like to see it, can give a complete and total answer onto the nature of time. Comedians can talk about the nature of time and offer perspectives on the nature of time and have an awareness and a sensibility of the nature of time that they can only see from their perspective as a comedian.
Right.
So at the end of the day, like, what is time?
Right. And to section it off and compartmentalize it will give each different compartment a lesser understanding of what this thing is.
Exactly.
Yeah, that's an interesting way to approach it. So for the Big Bang, for example, proposed by a Catholic priest, a Belgian priest, initially, this idea obviously intersects with physics as well as theology and religion, and every religion has, a creation story to some capacity. I always find it unique and interesting that, within Catholic and Christian tradition and Jewish tradition as well, the creation story tends to map fairly well with, human evolution and things like that, right? Like this idea of let there be light and a bang happens. So obviously that...
Well, there was no bang. I will push back on that.
Okay, explain that.
Like Genesis, there's no bang. There's just let there be light, and then there was light.
Right, but could there have been a bang?
I don't know. The Bible doesn't say it.
Right.
So you can't. If you want to play the game, and I have this distinct memory. I was with a group of people, and there was one guy who was so excited to finally meet me. He was a giant fan of the podcast. See me on TV. He's like, he sat down next to me. He's like vibrating. He's like, so. I think he starts off, I think Genesis and the Big Bang Theory are the same. And I said, I don't think they are. And he collapsed. I'm very sorry,
Why did you
guy.
do that, dude?
I'm sorry. I'm not here to make you, I'm not a therapist.
Right.
I'm like an anti-therapist. You have to work really, really, really hard to squint your eyes to make Genesis. And remember, there are two stories of creation in Genesis that are mutually incompatible. You have to work really hard to make one of those stories kind of look like the Big Bang. And you also have to like squint really hard to make the Big Bang kind of sort of look like Genesis. And then you have to add a bunch of stuff like the word bang in the ordering of events and the progression. And then even if you did, what do you get from that? Like, okay, let's say that the story of Genesis somewhat mirrors our modern understanding of Big Bang Theory, which it doesn't, but let's say it did. Well, now what?
Well, I guess from one perspective, you could say, oh, wow, these ancient philosophers and writers that wrote the Bible, perhaps they were divinely inspired, or perhaps they knew something about the universe that we didn't even really fully realize until millennia later.
Does that mean also that Edwin Hubble was divinely inspired?
Yeah.
I don't know.
Yeah, I don't know.
Okay, now that's a more interesting question.
Yeah.
What about all the religions who got it wrong? Should I stop believing in Hinduism?
Mm-hmm.
Because the writers of the Bible, again, they did not get it right. It's nowhere
Right.
near our modern understanding of Big Bang, but let's say they did. So are you saying, not you personally, but the mythological you, that if we should look to science and empirical methods in order to validate our religious beliefs? Because that's how you get Galileo under house arrest. I thought that was a bad idea.
Right. Oh, that's interesting. I guess to me, the feeling is that if these two ideas are compatible in some abstract way, this is a metaphor that the writers of the early Bible are using to describe this phenomena that may have been passed on, orally from generations, and they were able to possess this type of knowledge. And obviously, if you are following the Catholic, Jewish, Abrahamic tradition, you would look at this and say, oh, wow, we're on the right path, because this ancient text holds up to scientific scrutiny. And if God created science and also, this theology, they shouldn't be incompatible.
Just last week, I was in DC for a conference, a Department of Energy conference. And I drove down for some strange reason. I decided to drive my family. There is a train, and there are planes and all the wonderful marvels of modern technology. For some strange reason, I'm still not exactly sure why, I decided to drive my family down the Northeast Corridor, which took 8 hours and 45 minutes.
Kids in the car?
Yeah.
You're crazy.
Yeah, I am. So my wife and the kids flew back, and I drove the car back. Anyway, I parked at the Museum of the Bible, which I had never been to before and I've never heard about. I think it's new, although I didn't bother to look it up. And I happened to be walking by, and I saw through the window, they have various signs pointing to different sections. And there was a section that said Science and the Bible. And in that moment, I had an epiphany. I was not upset. I was not angry. I was not put off. I was elated, because I get to be a scientist. I am a scientist. And everybody wants a slice of that science pie. Science commands so much respect in the world that even the Museum of the Bible couldn't help themselves but tried to connect themselves and hitch themselves to the science wagon. They couldn't stand alone and just talk about the Bible and how awesome the Bible is and how powerful and influential the Bible is in the modern day world, which it is. They couldn't resist trying to connect it to science, and everybody wants to attach themselves to science. I'm like, wow, what a privilege that I get to be part of a profession that everyone wants to use to justify themselves. Like, there's not the Bible and car mechanics, and I have so much respect for car mechanics because they do such a difficult job. My car is in the shop right now. So if you're listening, Jim, I do respect what you do
because you do bad oil.
No,
you're getting bad oil.
You do a very complicated thing.
Don't listen to him, Jim. Don't listen to him.
Car mechanics do a very complicated thing that I barely understand.
Right. But we can acknowledge that in broader society.
But no one says like the Bible and car mechanics, and no one tries to use car mechanics to justify the Bible, but they are trying to use science. And like, all right. Like of all the jobs I could have picked and passions I could have pulled in this life, like that's awesome. Yay, science. Good for me. And then I got upset because it was super annoying to see something like that. If you need science to justify your religious belief, you're doing religion wrong. Just believe it, man. Like either you believe if you need empirical evidence in order to justify your faith, then you need to do some deep soul searching into the nature of faith and what it means to believe and what divinity means to you and what and the role that religion plays in your life. If our observations of the early universe and the evidence we have accumulated about the Big Bang rock your faith, then your faith is very weak. I'm sorry to tell you. Your faith shouldn't be about the physical history of our cosmos. 500 years ago, I give you a pass. 1,000 years ago, I give you a pass. But when you dig down to what faith is and what it means in your life, and there are 7 billion people on this planet, which means there are 7 billion different answers to that question about what faith, the role that faith plays in their lives. You don't need science. You don't need me. You don't need the Big Bang Theory. You don't need Einstein or time dilation. If you need that, then just take a breath and ask yourself what your faith means to you and the role it plays in your life.
Interesting. But I look at it as like, if there's 10 ancient texts, right? And 9 of them, the creation story is that, there was a mystical guy that came down and fornicated with a wolf and then created humankind or something. Yeah. I would say, these are interesting stories. And then if there's one that has detailed metaphor to explain the existence of all human life, and maybe is not using the exact details, but is able to understand and explain germ theory and radiation and the planets, and at a time when we didn't have a lot of scientific background, and maybe even has predictions about the future that have all come to fruition, I would look at one of them and say it's divine, and the other ones and say it's metaphorical. And if I'm looking at all of them and trying to assess which one is the most true and has the most validity, I would be drawn to the one that seems to hold up in the light of empirical science that we can test.
I would say, and this is the position of the Catholic Church, if you're reading Genesis wrong, that Genesis is not a literal story of the physical creation of the universe.
Right.
Even the Pope says that's not it. It's a metaphor about the human condition, and it instructs us that when we ask what is humanity's place in the universe and relative to the divine, it's not about our coordinates in the Milky Way galaxy and the billions of years since the formation of our galaxy and the agglomeration of elements that have created this world. There's a different way to answer that question. There are different shades of meaning to what is our place in the universe. It's not our physical place. It's our metaphysical place. It's about our relationship to God. It's about our relationship to each other. It's about what is the human condition and what generated the human condition and how can we make that human condition better. That is what the story of Genesis is trying to teach us. And still, the story of Genesis bears no resemblance whatsoever to the Big Bang Theory. I will throw down with you.
Okay, so let's say the idea that let there be light, bang. God,
no bang. You inserted bang.
Okay, all right. Let's say there's no bang. Okay, fine, there's no bang. Okay, then there's planets. Okay, God creates the planets. I think that's what I was like. And then
let's get Genesis out.
All right, let's pull it. All right, fine. All right.
Because
now we're playing poker. Okay, show me the river. Let's go.
Yeah.
I mean, this is so fun.
Genesis chapter 1, because there are 2 stories in Genesis.
Yeah, explain that. I'm actually not familiar with this.
So let's read it. All right, here we have a theoretical cosmologist quoting. What version do you want? Do you want the King Jimmy?
I typically go NIV. I don't need all these these
Okay,
and thys.
okay.
You know what I mean?
We'll do NIV. Genesis chapter 1, NIV. The beginning.
Technically, I've heard that Dewey Rames is the most accurate translation, but regardless.
Okay, first line. Genesis 1:1, NIV. In the beginning, God created the heavens and the earth. Well, that's wrong because the Earth formed 4 billion years ago, and our universe is 13.77 billion years old.
Okay.
Now the Earth was formless and empty. Darkness was over the surface of the deep, and the Spirit of God was hovering over the waters. So that's also wrong. Yeah, the whole solar system agglomerated from a gaseous nebula, but it was lit by the proto-sun well before the Earth glued together itself as a planet. So the sun was already illuminating the Earth before it formed. So darkness was not over the surface of the Earth. It was already illuminated.
Always.
Or at least like the proto-sun started, was a light, was hot and bright before protoplanets formed.
Mm-hmm.
And God said, let there be light. So in Genesis, the heavens and the earth and then the deep, which I'm assuming is the ocean. Fair enough. You can debate that if you want. Oh yeah, because the Spirit of God was hovering over the waters. So there are the heavens, there's the earth, and then there's water. Come before light. Because now God, this is Genesis 3, and God said, let there be light, and there was light.
Right.
So that's totally out of order.
Okay.
God saw that the light was good, and he separated the light from the darkness. Okay, I don't have much to say about that.
You just don't understand what that means. You know what I mean?
Oh no, it continues. So, he separated the light from the darkness. God called the light day, and the darkness he called night. Well, now we understand that light is just ever present, and it's simply illuminating another part of the earth, but the people who wrote this didn't know that.
Right.
And there was evening and there was morning the first day. That was nice. And God said, let there be a vault between the waters to separate water from water. Slightly confusing. I don't know. And so God made the vault and separated the water under the vault from the water. There's water in the sky.
Right.
So this is their cosmography, their map of the heavens. There's water way up high that occasionally rains down as rain. And then there's water here on the earth. They didn't realize it was all connected with one hydrological cycle. Presumably, if they had known that, they would have said that and said, and thus God made a hydrological cycle where
Precipitation.
Right. Yeah. God called the vault sky, and there was evening and there was morning, and that was the second day. So we're 8 verses in, and we're pretty much all wrong.
Okay. But I think it's going to really pull together in verse 9.
Okay, I should keep going.
Verse 9, it pulls together. I'm telling you, bro.
Oh, yeah, here it is. And then there was stellar nucleosynthesis.
See, I told you.
And the separation of the fundamental forces and the inflation. Wow,
See,
yeah.
You're a hater,
and
bro.
God
You're
said it was good. I didn't,
You were hating, dude. You were just hating. So you're not a therapist, right?
Horrible therapist. Please do not come to me for
You're an
therapy.
asshole, Paul. Come on,
I'm
dude. Let me believe it. Your shirt's ugly. I'm going to start just attacking.
Go for it. Go for it. I've heard worse. I have a YouTube channel. I read the comments. There is nothing that you can say to me that has not been worse I've seen
Okay, now I got to try.
On social media. No, but even if there was something that approximated our current understanding of the Big Bang, one, our current understanding of the Big Bang is provisional, and new evidence can and will supplant it. I hope 500 years from now, we have a different view of the history of the cosmos. It might look largely similar to how we understand it now, but it might have completely different language to surround it. And two, if there was a very, very accurate or quasi-accurate depiction of the Big Bang Theory in some mythology, I wouldn't use that use that as evidence to say maybe this mythology is more correct, because using science to validate religion seems a little off to me, in which case I would argue that you're doing religion wrong. I would say that there are common themes that arise in human thought over and over and over again. We are a creative species, but not that creative. Hero of a Thousand Faces, that kind of thing. We tend to tell the same kinds of stories over and over again. And the Big Bang Theory is ultimately a story. Yes, it's a story based on evidence. Yes, it's a story that we strongly believe because of that evidence, but it's still a story. It's a myth. It's a different kind of myth. It's a scientific myth, which is new in human storytelling. But I would use that instead to say if there was some sort of commonality, and there are commonalities. I've actually written about this in the past, how you can see echoes of the Big Bang Theory in religions across the world and throughout time. That there are only certain kinds of stories that we can tell as humans, and they take many different manifestations and many different shades and many different forms. But I would just say, well, yeah, the people who wrote that story thousands of years ago, they are just as human as Lemaitre was when he created the idea of the primeval atom, which is the predecessor to our Big Bang Theory. Just as human as the people who work on the Big Bang Theory today. And we're just telling stories around the campfire.
It's kind of relieving in a way, right? To have this idea that we understand more things now because there's more scientific evidence, but we're not intrinsically more clever than we were 1,000 years ago.
No, we're just as smart back then. Just as smart.
Just with less data downloaded into our brains.
Exactly.
Or maybe different data, actually.
Different data. Yeah. Like, I don't know where I was going with that thought, but yeah, no, that's a valid thing to say. Like, we were just ingesting different kinds of data and interpreting the data. Listen, our universe is weird and confusing, and we find ourselves existing in it. And we are compelled. Part of our human nature is to try to explain that world around us and try to explain our existence within it. Science is one way of doing that. It's a very powerful way. It's a way I love and work at as a profession. But it is just one way.
So this idea of the Big Bang Theory, do you subscribe to it in any professional sense? Do you entertain it, obviously, through...
Absolutely. I am a theoretical cosmologist. I study the Big Bang. I study the early history of the universe. I study the contents of the universe. I try to understand the ultimate fate of the universe. This is my day job. That and talking about science, which I really enjoy doing.
Do you find that idea makes sense, that there was a bang of dark energy, dark matter that created all things and created this expansion of the universe?
Let me answer that two different ways. Most scientific statements, including the Big Bang, including evolution, germ theory, the heliocentric universe, only make sense because we're used to it. And only makes sense because the weight of evidence has forced us to believe it. If I were to transport 2,000 years ago and start talking about quantum mechanics, they would probably arrest me and lock me up because it's nonsense. The statements we make in physics are, wait a minute, you're saying that that deep in the hearts of stars, there are these things called hydrogen atoms that smush together and release a little bit of energy, and this powers the star and generates elements in the periodic table, and then the stars die, and then that's crazy talk.
Yeah, it is absurd.
When you take it out of context and just isolate it, it's absurd. But we have all the evidence to support statements like that, so I guess we gotta kind of believe it, whether it makes sense or not. This is one of the powerful things about science that I find about science, is it gives us the freedom to make statements that are totally nonsensical and weird and crazy, but also probably right. It liberates us from the constraints of having to make statements that only make sense. We get to say things that don't make sense, but the evidence points us in that direction.
It's a wave and a photon. And you're like, all right.
Whatever.
I guess it's both.
I don't get it. Nobody understands quantum mechanics. And if someone says they understand quantum mechanics, just slap them because they're lying to you. They are lying to you and probably trying to sell you something. The Big Bang does not make sense. It was not an explosion in space. It was not some boom over there. The Big Bang happened everywhere. in the universe, because the Big Bang was the universe, and the universe is by definition all the things. So there can't be something outside the universe, because that's one of the things, and that has to be part of your universe. The Big Bang was not an explosion in space, and it was an explosion of space. Where did it come from? When did it start? How did it start? I don't know. I don't know. I don't know. I don't even know if those questions even make sense, because we are at the limits of human understanding. I cannot envision the earliest moments of the universe. I cannot envision the act of the Big Bang. I cannot picture it in my mind's eye. I can write about it mathematically. I can describe the physical effects of it and the observational consequences of it, but I can't imagine it. That's another wonderfully powerful thing about science, and especially mathematics. It allows us to grapple with concepts that are literally beyond our imagination. Because the mathematics and the evidence force us to these conclusions. I can't tell you what the beginning of the Big Bang was like. I can't tell you if the word beginning even makes sense, because we're talking about the creation of time itself, possibly. So what does it mean to be before the existence of time? That's a weird one. Yeah. I don't know. Nobody knows. We might have some answer down the road. It'd be nice if we did, but I'm sure that answer would be followed by a dozen questions. I can't hold these concepts in my head, but I can grapple with them mathematically, and I can grapple with them scientifically. And that's a wonderful gift that science gives us, is the ability to probe into areas of the natural world that are otherwise unbelievable.
So it's not really worth my time as a layperson who's not dedicating my life to this to try to envision what that was like.
Of course it's worth your time.
But if you can't figure it out, why should I figure it out?
Because it's fun to try. That's like saying, I shouldn't try to understand this song that speaks to me. Is making me feel this way. You can let it wash over you, or you can also inquire into yourself. Why does it make me feel this way? It's fun to think hard thoughts, at least for me.
That's how I feel. That's how I fall asleep. I'll lay in bed and I'll try to imagine what the Big Bang was like, and then it'll tire me out, and then I wake up the next day.
Yeah, that's fun. That's human curiosity. Trying to think the unimaginable, the unthinkable. Trying to imagine, what does it mean for the entire universe to be birthed in a moment that created itself? Like, what does that mean? This is the joy of human creativity. And these are the kinds of questions that philosophers and scientists and theologians and musicians and artists and poets have been grappling with for eternity, for millennia.
Now, there's something that you said in, I think it was your interview with Wired, that was a great question that I'm so curious if you can like expound on, but this idea that the universe is expanding. What is it expanding into?
Oh, I love this, because this gets right to the heart of what we were just talking about. It's tempting. When you think of an expanding universe, you think of galaxies flying apart from each other, which is how we measure it and how we know the universe is expanding.
Like a shock wave of an explosion.
Yeah. And it's like a bunch of shrapnel. And you think of it like an expanding ball of shrapnel or an expanding balloon. But then wait a minute. You ask, well, what is it expanding into? And if you imagine it as an expanding ball of shrapnel or a bunch of bees flying up farther apart, they're expanding into something. Empty space, vacuum. But the universe is by definition all there is. You can't have a barrier to the universe, because what is a barrier? A barrier is a separation between one side and another side. But the universe is all sides. The universe has no boundaries. It has no barriers. It has no edges. Because an edge means there's something after that, and that has to be a part of the universe itself. The universe is expanding, but it's not expanding into anything. And I don't mean, when I say anything, I don't mean vacuum or void, because that's a thing. I mean, the question makes no sense. The universe is simply getting bigger. The average distance between galaxies grows with time. And that's it. It is not expanding into anything. It is not expanding from anywhere. It's not going anywhere. It's not coming from anything. The universe exists. It is the entirety of existence by definition, because that's what we call a universe. And the average distance between galaxies is growing with time.
Could you compare it to a balloon? That as you blow into a balloon, the balloon expands.
I cannot.
Why not?
Because the balloon is expanding into what?
Into the space around it.
Into the space around it. But the universe is all the space. There is no such thing as outside the universe. And you know what? I can't imagine that. I cannot picture it in my head what an expanding universe looks like. But I can simultaneously say with an extreme amount of confidence that the universe is expanding. Because we've observed the distance between galaxies growing on all scales, peering back billions of years.
Is that not frustrating to you that the question doesn't make sense, but the math to prove the phenomenon
But I
makes
can
sense?
still have an answer. Yeah. It is simultaneously frustrating and joyful and rewarding and satisfying because I'm in a very privileged position, a very lucky position as a scientist, that I get to ask questions that do not have easy answers. And I get to ask questions that don't have simple, straightforward answers. That's why science uses mathematics. Mathematics is a tool that allows us to grapple with concepts beyond our imagination. Just like a hammer is a tool that allows me to build things that I can't with my bare hands. Mathematics is a tool that extends my thinking. It extends my consciousness into areas of thought that I can't immediately access with just my imagination or just by thinking about it. We see this all through the sciences. Especially physics, I can't imagine, literally can't imagine what happens at a subatomic level. What is actually happening between electrons and nuclei inside of an atom? I can't picture it. No one can. But we can make a theory of it. That
Right.
very powerful theory called quantum mechanics that explains how the universe works. I can't imagine what the universe is expanding into, but I can talk about it and I can write it down mathematically and I can look at the consequences of what an expanding universe, how it ought to behave, and I can look for evidence to support that and I can find it. That's fun.
Yeah. I wonder if there will become a time where these ideas that plagued scientists of 1,000 years ago, they were on the edge of what they could comprehend as humans. Maybe this is giving us too much credit, but the idea that these scientists were dealing with things that were so difficult to understand that now it could be fifth grade math. This idea of like Pythagoras' theorem was at the time groundbreaking mathematics.
Oh, it was a whole religious movement, literal religious movement.
Oh, really?
Yes.
I didn't know that.
Oh, there was a whole cult. The Pythagorean theorem is not named for Pythagoras, the person, but for the Pythagorean cult that he had started.
Oh, I didn't know this.
Oh, it was a whole, oh yeah, if you worship mathematics, this is the divinity. This is the root of all existence, or these divine truths. Look at this. You can write down a thing, a statement that is always true. Is that not God?
Oh, how interesting. And now you learn it when you're in fifth grade.
Yeah, and then forget it in sixth.
Yeah, I mean,
Yeah. Oh, yeah. We become ever more sophisticated with mathematics. We become ever more educated. We are teaching stuff to our children that even was not taught to me because it was not deemed worthwhile or useful. Like kids are learning algebra
Right.
in seventh grade. It's like, wow, I didn't learn that until high school.
Right.
I hope our descendants have more sophistication in mathematics, more sophistication in philosophy, more sophistication in faith.
Mm-hmm.
Faith has not stayed static. There's this caricature that faith doesn't change, but the Catholic Church of today is different than the Catholic Church. Some things stay the same, but certain shades and emphasis have changed over 1,000 years. No, faith changes, philosophy changes, mathematics changes, science changes. I hope that our descendants view the cutting edge of science today as elementary school topics.
Like imagine if your great grandson is learning Einstein's general theory of relativity.
Yeah, in like fourth grade.
And it's like, oh yeah, of course, this is what it is.
And I hope it's continue with, okay, now that we taught you that, here's the real deal. Here's what they learned. Here's what they learned and believed as cutting edge scientists in the 20th and 21st century. And here's how we've progressed since then. The same way we talk about Newton. And say, oh, yeah, Einstein's general relativity has certain applications. It's very useful. And then here's the next step.
Right.
I hope.
Yeah. I mean, especially this idea of quantum mechanics, to me, just on a very, broad tertiary level, just seems to break everything that I've ever learned, right? You learn these rules of physics, and you're like, okay, can't be created or destroyed, equal and opposite reaction, locality, all this shit.
Yep.
And then all of a sudden, it's like, nope, superposition. It can be two things.
Sorry.
It's like, what?
Yeah, it turns out that the subatomic world does not play by our rules. We thought it did, but it turns out it doesn't. We've created an incredibly successful theory, a series of theories called quantum mechanics, to encapsulate the rules that the subatomic world seems to play by. And these are directly and manifestly contradictory with our common sense, rational understanding of the macroscopic world.
Could you explain just like a very basic understanding of like superposition and how it like would like show up in like a scientific trial?
So superposition can take many, many different forms. One form that it takes is that we're used to things in the macroscopic world being binary. Either it's on or it's off. The glass has water in it. The glass doesn't have water in it.
Alive and dead.
Or it has this much water in it. Not a little bit more, not a little bit less, but I'm looking at this bottle. It has precisely this much water in it. We're used to, in the macroscopic world, being able to make definitive statements. This or that, X or Y, A or B. This much, not that, no, but that.
It exists right here.
It exists.
It's not more there. It's not more there.
The bottle is in this position on the table. It's not over here. It's not over here. It's right there. Superposition breaks all of that. Turns out subatomic particles like protons, electrons, etc., can be in multiple places at once if they want to. Can have multiple states if they want to. Can take on different values of energy, position, momentum if they want to. And we can concoct experiments that force subatomic particles into superposition states where they have all available positions, all available energy values, all available states simultaneously. And then when we go to observe the particle and actually measure like, hey, electron, where are you? It appears in one specific spot with one specific energy level. And then we stop looking and then it spreads itself out again. We do not understand how this works. We do not understand why the subatomic world behaves this way. All we know is that this language that we have developed, this nonsensical language, works.
Yeah, I just want to reiterate that point because that is the most fascinating thing in the world to me, that a particle, whether it is being observed by a person
or an instrument or participating in some interaction,
it's the nature of the observability will change the state that it is, or the location, or a litany of different things. Just the observation of it. Whether we're looking at this bottle or not, that bottle is right there.
Yeah.
But on a quantum level, that is not the case.
Exactly.
And that is just so crazy. And the idea of Schrodinger's cat, which I think a lot of people hear, but they don't really necessarily understand, is that this is taking this micro idea and turning it into a macro idea.
Exactly. And this is the story of Schrodinger's cat is fascinating. Erwin Schrodinger was one of the founders of quantum mechanics, the early pioneers, developed a wave equation that described the motion of the behavior of subatomic particles, would end up detesting this newfound theory of quantum mechanics that he helped create. Absolutely reviling, to the point where you can read his letters, and he is getting, as the years go by, he is getting meaner and meaner and meaner and using more and more swear words in his letters until the point where he just quits. He just stops working on quantum mechanics because he is so disgusted by it. And one of the points he makes, he says, okay, you talk about electrons and superposition and occupying multiple states and the primacy of observation and how this changes, reality upon observation. Let's take a thought experiment. He got this idea from Einstein, by the way, who also detested quantum mechanics. So, okay, let's put a cat in a box. Why not? Do it all the time, I suppose.
Yeah.
It's Germany.
It's a different time.
Different time.
Yeah.
Put the cat in the box and then set up some contrived way to give it after an hour, to have a 50-50 chance of killing the cat. Like maybe it's a radioactive isotope that has a 50-50 chance of decaying. It doesn't matter. There's just some random chance involved. So now you have set up a quantum probabilistic system. According to quantum mechanics, our understanding of it, what goes for electrons goes for cats. You put the cat in the box, and as long as no one's looking, the cat is in this superposition state of both being dead and alive at the same time. Not dead or alive, and we just don't know. No. Quantum mechanics says it is both simultaneously. And then when we open the box, it's not a matter of us finding out. It's a matter of us creating. The act of observation creates a dead cat or creates an alive cat. Schrodinger said, "This is stupid. You are idiots. You are obviously missing something, but you're so far up your own rear ends that you can't see that you are building a ridiculous theory of nature." The argument against Schrodinger, as championed by people like Bohr and Heisenberg, which would become the dominant view of quantum mechanics, was that, well, of course, Erwin, it doesn't apply to cats because cats are macroscopic objects. They have hearts, they're breathing, they're interacting. Like, of course, so trying to bring this up to the level of cats is stupid. We're going to keep it down to the level of electrons. And yeah, why should subatomic particles behave in a way that we can comprehend with our imaginations? Why should it make rational sense? The universe is under no obligation to make rational sense. The universe just does what the universe does.
But aren't there laws of physics that these subatomic particles should be operating by?
Yes, we call quantum mechanics.
Okay.
And the laws of quantum mechanics are different than the laws of macroscopic physics.
They should have told me that.
They should have
been
a sign on the door.
Yeah, laws of physics mostly.
Yeah, laws of physics up here and then different laws of physics down here.
Yeah.
Somewhere there's a transition between the two. We don't know where or how or why. But just definitely when you get down to atoms, it's totally quantum mechanics rules. And then when you get up to people and cats, it's definitely like Newton and thermodynamics and stuff, all the classical physics. But it's just different. It's just different in that the universe is under no obligation to be sensical. It's under no obligation to match at all scales. And you should just get over it.
Yeah. But it does break your brain a little bit.
It does break your brain, and it does introduce an element of frustration, which has infected all of quantum mechanics in the centuries since it's been invented, which is, yeah, Heisenberg, I hear you. Like, there's no reason to suspect that, an electron should behave in a sensical way, but are you sure? Like, are you sure? Are you sure? Maybe, and this was Einstein's argument, electrons do behave in a sensical, rational way, but we're not clever enough yet to figure that out. And so we created quantum mechanics as this kind of stopgap measure to explain observations, but there is a deeper theory hidden underneath it that we have yet to discover.
And what do you think of that idea?
Well, here we are, 100 years later, quantum mechanics has survived every single experimental test we've thrown at it. A lot of Einstein's finer points have been disproven. His arguments against quantum mechanics have been countered successfully. His objections still stand, however. One of Einstein's biggest deals about quantum mechanics was that it appeared to be non-local, which means you can do something over here and it will have an effect over there, regardless of how far away they are, that seem to violate like common sense rules about the universe, that if I do something here in the universe, it should only affect the stuff in this room. Like someone living in the Andromeda galaxy shouldn't really be caring about what I do. And yet quantum mechanics says we do. Einstein's argument was that if you're going to make that leap, if you're going to say quantum mechanics is fully non-local and yes, we're all connected, man, then how in the world can you claim to believe the result of any experiment? Because the whole point of scientific experiments is to isolate. So you can say, I run this particle collider, make this prediction, I get this result.
Yeah.
But simultaneously, you're saying, well, in quantum mechanics, everything is connected. And there's some random hydrogen atom in the Andromeda galaxy that flipped upside down yesterday and has an influence on this hydrogen atom over here in my experimental apparatus. Then how can both be true?
Right. Faster than the speed of light. It violates
everything. Yes. How can that be true? How can you have non-local physics and yet claim to use local experiments to validate your theory?
Right. It has to be repeatable. It has to be predictable in some capacity. It has to be
predictable and it has to be isolated. Like we design our experiment and isolate it so that we get one cause and one effect. So we can test that cause. We can test our hypothesis. But now you're saying the whole universe is connected at this weirdly fundamental level. Well, how do you know your experiment was truly isolated?
You can't prove it.
You can't. Einstein would go to his grave making that argument. And honestly, no one has come up with an argument against it. We now know that the universe appears to be non-local. What quantum mechanics says about the universe does appear to be true. And we also believe our experiments to be isolated and replicable.
Yeah.
Einstein was viewed as this, like, towards the end of his life, as this doddering old fool that had lost touch with, the direction that physics was going. But the people who say that are the people who disagreed with him and outlived him. So of course they're going to say like, yeah, I totally told that Einstein guy, who's boss.
Yeah, right.
Yeah, it turns out Einstein had made very good points that were simply ignored.
Right. Yeah, I mean, the locality thing is really fascinating. Could you expand? I know very briefly this idea that if you're observing, one electron, and if it's rotating in one direction, another one will be observably rotating the other direction. Can you expand on that idea?
Yeah. So this is going back to something called entanglement, which was actually discovered by Schrodinger and then immediately reviled by Schrodinger, who pointed to the existence of this phenomenon called entanglement, which we're about to entangle ourselves into. He pointed to it as a symptom of a disease inside of quantum mechanics that showed that this was an incomplete theory. He was shouted out of the room. An entanglement goes like this. As an example, there are many, many different ways to manifest entanglement, but the simplest one to think about is to take, say, two electrons. And I can prepare them in a special way, which means I get them close to each other and I look away. And they have a little baby electron. No, I'm just kidding. They entangle themselves. That means I can no longer consider it as electron A and electron B. There is now, when they are entangled, one common equation, a mathematical expression that describes both of them simultaneously. And it's not just the mathematical expression for the first one and then plus the mathematical expression for the second one. Through quantum mechanics, through Schrodinger's work, we realize, no, there is one equation that describes both of them at the same time. This connection, this entanglement between them, doesn't care about distance. Like the distance between the particles simply doesn't appear in the mathematical expressions. That means I can take these particles, separate them. I can give you one of them, and I can keep one of them. We're not going to look. We're not going to look. And we can get very far apart. On the other side of the room, on the other side of the planet, on the other side of the galaxy, it doesn't matter. And then I can finally, lose my patience, and I can look at my electron, and I can measure its state, measure its properties. And just based on that one measurement, I can instantly know, because they're entangled, what your electron is like. Instantly. And this is where Schrodinger and Einstein said, "Are you insane? You have made no observation of that electron. It has sent no light signal to you. You have not communicated with, you didn't call me up on the phone. And yet you somehow, through quantum mechanics, you are able to know precisely 100% perfect knowledge of the state of that electron, no matter how far away it is in the universe. And you don't even need to look at it." This drove them nuts.
As it should.
As it should. And then the response of Heisenberg and Bohr was, well, too bad the universe is mysterious. Which works.
Is true.
I mean, it's true. And works, but is, it's like eating a whole bag of chips in one sitting. Like you're full, but like not necessarily satisfied, and you feel a little greasy afterwards. And so quantum mechanics has developed over the past century as a very successful theory. And we validated this with experiments. Like we can separate the electrons, and then you open up one and say, I know what the other electron is. And then you go to measure the electron and you're right.
Yeah.
Again and again and again.
Faster than the speed of light,
Yeah.
faster than Wi-Fi, faster than anything that exists.
Instantaneous.
Yeah.
Because they're connected at this weird quantum level that we do not understand. So it's verified by experiment, and yet we cannot explain it. Quantum mechanics, it's like one step above what we were just talking about with the Big Bang Theory and the expansion of the universe, which are both also experimentally verified. It takes it to another level. Like there's this entire class of physical phenomena happening every single day all throughout the universe that we know happens, and we can describe mathematically, and we can make predictions, we can do science, and yet we can't explain how it works. I cannot sit here in front of this microphone and tell you how entanglement works, and nobody can.
Or also slap them.
Or slap them because they're trying to sell you something.
Yes.
Nobody can do it.
Yeah. But now, like we were saying with the intersectionality of all these different things, right? We're able to prove this thing on a metaphysical level. And maybe we need theology or philosophy or some other type of discipline to enter in to try to complete this picture.
Absolutely. Why not? I mean, we can experimentally, I won't say we proven it because nothing in science is proven.
Sure.
We only experimentally verify, and tomorrow there can be an experiment that invalidates all of quantum mechanics.
Einstein's right and we're idiots.
Yep. And we can validate that this is a feature of our physical universe that we do not fully understand. Maybe there is a deeper theory to quantum mechanics. I don't know, we've been trying for 100 years and we haven't found it. Maybe we're missing something about our interpretation. Maybe we are, maybe we're so focused on the mathematics and various interpretations that we're missing some perspective. Maybe, this is just me spitballing in the moment, maybe because we've compartmentalized science so much and we've lacked so much other perspective that that humanity does have the capability of understanding this and grappling with it. We do have the language, but that language hasn't entered scientific circles yet. I don't know. Maybe it's a poet understands this at a deeper level than a scientist does, and hasn't realized it yet.
I mean, you hear jam bands talk where they say, I know what you're thinking. There's a telepathy that's happening. I can know what sounds you're going to play before you play them, and I can play them in conjunction with you, and we create this beautiful harmony without talking. Just talking on some type of metaphysical brain level. They say this all the time. I heard musicians talk about it. Fish talks about it.
I don't know if this quantum manifestation of entanglement has other manifestations that we are aware or not aware of. I don't know. I don't think so, but also I don't know.
Mm-hmm.
But I also know that our understanding of entanglement is lacking. We have no words to describe it. We have no mental image to describe it. Maybe somebody does.
Mm-hmm. So now, hypothetically, and you had kind of poked fun at this before, but I'm curious what you think. Like this idea when people do psychedelics, they'll do mushrooms. There is a stereotype of people that do high doses of psilocybin, and they'll say everything is connected. The universe is connected. I'm connected to you. We are all books on the same bookshelf. We are connected. And then, and they've been saying this for however many years people have been doing psychedelics in Central America, and obviously now since like the 50s through the psychedelic revolution, people have been saying we're connected. And then all of a sudden quantum mechanics comes along and it's kind of like, these hippies are kind of right. You know what I mean? Like it is a little wild that these people have this feeling through the substance that then kind of gets scientifically verified, which again is sort of like entering into this science religion conversation. Right. But I'm curious what your thoughts are as to that, you know, both as a scientist, but also just as a guy that's curious.
Yeah. You know, it's one thing to say we're all connected. It's another thing to say how and why and what are the implications of that. So yeah, we're all connected in this quantum mechanical entanglement sense. Quantum mechanics also tells us how we're connected, and how electrons can be entangled with each other, or all subatomic particles can be entangled. It also tells us that at macroscopic scales, the entanglement gets lost and confused. I can entangle 2 electrons, but I can't entangle 1,000 electrons. There are too many interactions and too many random motions. The entanglement breaks down.
Scientifically verified.
Yes. Or at least another way, another perspective is that, yes, they are entangled. Like in one sense, all the particles of the universe are entangled with each other, but to such a complicated degree that it's essentially meaningless, that the word entanglement loses its force at macroscopic scales. And we also know that. But we also, there's a lot of unknowns. We do not understand the full implications of what entanglement means. We barely understand the theory or the idea or the concept itself. So, okay, good job, hippies. You discovered that we're all connected. Now what? Well, I have some follow-up questions. How are we all connected? I don't know. Well, what are the manifestations of that connection? I don't know. I can tell you subatomically what the manifestations of entanglement are. I cannot tell you macroscopically, and I'm not entirely confident that there are manifestations at the macroscopic level. There's more to learn. There's more to learn, and there are more voices to be included, and there are more inputs to be had. If we've discovered as scientists aspects of the world that we cannot adequately describe or understand or wrap our heads around, I feel like we are obligated to start asking other disciplines of inquiry, starting with the philosophers, because science is a branch of philosophy. It's just a kind of philosophy. I have a PhD. That's philosophy doctor. That is, yeah, I'm a scientist, but my degree is doctor of philosophy.
That's why I thought you had studied.
Yeah, because all PhDs,
philosophy.
all PhDs are doctors of philosophy, just different kinds. We call them like physicist or biologist or chemist.
That's the PH of PhD.
Exactly.
Interesting.
We're natural philosophers. We are philosophers of the natural world. And we've developed this very powerful technique of inquiry, but it does not sit supreme to other ways of inquiring about the natural world, and does not sit alone or alien from them. So yeah, philosophers have been engaged in debate for 100 years as to the meaning of quantum mechanics, and they have engaged with physicists. I wonder, and I say this as someone who is married to a modern dance choreographer, I wouldn't look to a musician or a poet to understand entanglements in the same way that I understand it as a physicist, or to explore the physical manifestations of it or implications of it. But maybe I could look to a musician or a poet to get a different way to look at it, or to think about it, or to wonder about it. That might give me, selfishly, someone who's trying to understand the physical world, a way. to think about it in a different way that might be useful or powerful.
Have you heard any theories about how these subatomic principles could manifest in the macro world that you thought were, somewhat compelling or even just interesting to entertain?
It's actually a fundamental component of quantum mechanics that quantum mechanics goes away at the macroscopic world. We call this the correspondence principle. And it's baked into the mathematics of quantum mechanics. It is part of the theory. You actually can't escape it. And it's there for a very specific reason. It's there because the subatomic world is largely inaccessible to us. We can only get to it through high-powered experiments. And a lot of experiments, you need to run like particle colliders a lot of times in order to build up statistics of results. And ultimately, you, me, our computers are all macroscopic devices. We are macroscopic creatures trying to interface with the subatomic world. So if our quantum mechanical theories only lived in the subatomic world and only had subatomic consequences, we couldn't access it. We couldn't discover it in our experiments because ultimately our experiments are macroscopic. Eventually they reach a macroscopic scale. So the subatomic world has to interface with the macroscopic world, or it has to smoothly transition into the macroscopic world. And there are an infinity of possible ways that the subatomic world could express itself at macroscopic scales, where all these superposition and entanglement and uncertainty, there are an infinity of ways that could manifest itself in our macroscopic daily experience. As part of the bedrock of quantum theory, we deliberately chose one way, that the subatomic world eventually becomes the macroscopic world. We call this the correspondence principle. And that way is that when you scale up, when you introduce a lot of subatomic particles, when the interactions get frequent enough, if you run enough experiments, you recover standard macroscopic physics. You must recover. Because standard macroscopic physics, and I'm talking like Newton's laws, thermodynamics, have been experimentally verified at the macroscopic world.
Right.
We know Newton's laws work. So we know that subatomic processes eventually have to transition into the normal, familiar macroscopic rules of the universe because we've tested that end. We've seen that and we've measured that. And so it's baked into the fundamentals of quantum mechanics itself that this is how the connection is made. That if you imagine, well, okay, there's entanglement and superposition, that's super weird. And then it leads to some other macroscopic effect. Well, we'd be able to measure that because we've become very adept at measuring macroscopic physics, and we have for centuries. It would appear as a modification to some experiment that you could devise. And we have observed no such deviations. So we know it's both baked into the mathematics and the theory itself is that somehow all this weird quantum stuff eventually becomes the ordinary world. We cannot say how. We don't understand the mechanism behind the correspondence principle, but it appears to be correct.
Is the correspondence principle arbitrary?
Yes. It's arbitrary in the sense that you could choose some other correspondence. You could say, okay, all this weird entanglement, super weird stuff, leads to different physics in the macroscopic world, a different set of physical laws. Like maybe Newton's law is pretty much correct, but off by a little bit. And people have explored this. Because if it's off a little bit, then maybe there is some quantum shenanigans happening there, bleeding into the macroscopic world and in a way that we hadn't known before. But dang it, we've tested Newton's laws to 1 part in 16 or not 1 part, one part per trillion. Like, we observe no deviations from it in the experiments we've devised. And so this arbitrary guess of the correspondence principle that whatever weird stuff is happening in the subatomic world, and believe me, it's weird, eventually gives way to normal, well understood macroscopic physics seems to be correct.
But it does exist just as a preservation of macroscopic physics.
Yes.
Ultimately.
Exactly. But if we were to see, if like we were to wake up tomorrow and we would just start developing experiments where like thermodynamics started behaving weird, or tests of Newton's laws started behaving weird. Okay, folks, let's start talking about the correspondence principle. Maybe there's weird subatomic interactions that are leading to this.
Right. But and these ideas of like, you know, that people in the common world would describe and try to attribute quantum mechanics to, like, you know, telepathy or, you know, something happened to my mother and I felt it because we're entangled in some type of like cosmic metaphysical way, those experiments would have to be repeatable and observable in order for them to constitute underneath this macro umbrella of quantum mechanics.
Exactly. And quantum mechanics itself says, no, you can't do that. Like, because
arbitrarily.
Arbitrarily, but like the way we have constructed quantum mechanics, and this works both ways. It's not just, okay, let's recover the macroscopic world, please, out of all this nonsense. The correspondence principle also goes in the other direction. It helps us interpret quantum results. It says that if you run enough experiments, the average will be some classical result. Like, I shoot electrons down a strong magnetic field, and they have a choice because of quantum mechanics. They can go up or they can go down. Classically, according to Newton's laws, they should go straight. Well, I run the experiment a bajillion times. Half the time it goes up, half the time it goes down, average out, straight down. That's the correspondence principle. The correspondence principle helps us interpret quantum results. So it cuts both ways, reinforces in both directions. It is just a guess, but ultimately all of physics is just a guess that turns out to be right, or at least right so far. And if you say, well, quantum mechanics explains this extra aspect of reality, quantum mechanics comes back and says, no. Quantum mechanics, like the actual mathematics of quantum mechanics, says all you get is the normal universe that you're already familiar with. You don't get extras. If you want to create extras, you're free, but you need a brand new theory to describe that. People are connected in very deep and poorly understood ways. I don't think quantum mechanics is the avenue to understanding those kinds of connections, because the word connections doesn't always mean physical or even metaphysical. I'm connected to my family, but not physically connected. I'm not like holding hands with them in this moment. And I don't believe I'm metaphysically connected to my family. But I do feel emotionally connected to my family. Isn't that a valid connection? Isn't that a real thing? Like, my emotions are real, my family's emotions are real, and we are connected to each other. We respond to each other. We move in sync in interesting ways because we've lived together for so long and we know each other better than we know anybody else. Those are real connections, and we don't need to appeal to metaphysics to explain that connection. It can just But on the other hand, we don't need to appeal to quantum mechanics. You don't need to go in that direction. You can just say we're four people, or you know, we're a group of people who love each other and live with each other and spend time with each other and are connected in that way. Isn't that enough?
It just would be cool if it all worked out, though. You know what I
Because
mean?
everyone wants a piece of that science pie. Because everyone wants science and quantum mechanics to explain the world, but yeah, you're not going to get it.
But it is explaining a lot.
It is explaining.
And it is
sure.
It is so cutting edge.
Absolutely.
The seduction of trying to explain, you know, the way we feel about things and to sort of induce it, to make it into our regular lives is really, because a lot of science thus far has done that, right? Like, you know, before, you know, we would think that the sun was rising and the earth was stationary, but then we actually realized it's not. And now that informs the way we're looking at the world.
Absolutely.
And, you know, that I get a sunburn, and maybe I thought that it was a punishment from God, or I would get a disease, and I would think that it's, whatever, a lightning strike would happen, and it's Zeus. But now we know that it's actually sort of scientifically explainable things that are impacting my macro world.
Right, absolutely.
And that makes us feel good.
Although to respond to this, I used to think that lightning was Zeus, and now I know it's an electrical discharge. Maybe it's still Zeus, but this is just the mechanism he's choosing.
Right.
Right. Like there's always room for faith and theology. And I do not believe that science is here to displace faith in our world. Science, that's not the goal of science. That's not why I wake up every day. Being a scientist is to let's get rid of God. All right, folks, back, what do we got to crack today? So there's no more God. And that's not the point. And that cheapens science. Science is here to delight in the exploration of the natural world. And I feel like we're doing a pretty good job, and we have a lot more to learn. And what we learn about the universe can diminish your faith if you wanted to. It can also enhance your faith if you wanted to. It's silent. It has a different goal. It has a different purpose. And the world can still be full of wonder and mystery and beauty that we can sense and understand at a very human level. And if you try to use science to take away all the wonder and mystery, I don't see much joy in that. I enjoy living in a world that is full of mystery. Some of those mysteries I try to explain with science. That's literally my job. Other mysteries I don't try to explain through science, or I don't try to explain at all. I just allow myself to exist in the mystery and the joy of being alive in this universe and what it has to offer. And that's good enough for me.
Did you used to try to explain everything through science? Was that like a childhood or like adolescent hubris?
I was a teenager once. I grew up Catholic. I'm not Catholic anymore. And there was a period of my life that I was extremely anti-religious. And I was very interested in using science to attack religion, to attack faith, to displace religion, where I did believe in this very simplistic view of the world where you either have a faith-based perspective or a empirical-based perspective. And that's, now I understand that to be rather pointless. I used to believe that science would have all the answers. And if we don't have all the answers now, then soon enough, just give us more time. We don't have enough funding yet. But now I haven't returned to faith, but I also don't believe that science is equipped to answer all the questions that humans face. Like, what happened before the universe? What is love? What is time? What is nothingness? What is the difference between something and nothing? There are innumerable questions we can ask. How do I live a just life? How do I be a good parent? A good husband? A good son? What is the best way I can live my life to bring joy and beauty and goodness in the world? I don't look to science to answer those questions. Now, things we learn in science can inform those questions for sure, but that's certainly not the entirety or totality of the answer. And that's okay.
On a personal level, do you believe in God?
That is not a question that I discuss publicly. That is something, my personal faith or lack thereof is something I only share with my closest family. I simply do not broach that publicly.
Interesting. Okay. We can cut that out of the episode.
No, leave it in and leave in my answer.
Okay,
yeah.
Cool. Oh, that's so interesting. It is nice to be able to draw a line. I feel that feeling a lot where I'm wanting an explanation for things. And you know, if I'm at a funeral and someone passed away and their favorite bird is a cardinal, and when they are lowering the casket, a cardinal lands on a branch nearby and it brings everyone peace. Part of me is like, nah, it's nothing. It's just a coincidence, and there's birds in the area, and it's the season. And if we did this in the wintertime, there'd be no cardinals, whatever. But then also there's part of me that's like, well, maybe on a quantum level, there's an explanation for this. But I still am always looking for an explanation, and I'm uncomfortable with the feeling of it just is a poetic thing that happened.
Yeah. I share that drive of curiosity. That is what motivates me as a scientist. I do want to understand the world. But I am also humbled by the enormity of the cosmos, both physically and metaphysically, the wealth of things that we experience on an every single day level that we do not fully understand. Some things don't have immediate explanations. Some things don't have easy explanations, and some things have no explanations. Scientists, like in my career, I've been a scientist. I got my PhD in 2011. And I was researching before that. So I don't know, nearly 20 years I've been a scientist. One of my major questions, for example, is what is the nature of dark energy? This mysterious force that is accelerating the expansion of the universe. I don't think I'll ever know. I don't know if the answer will come in my lifetime. And there's a certain humility to that, to asking questions that are beyond yourself, to being a part of a journey, part of a progress where I have contributed and hope to contribute in the future and progress to this question. But knowing that likely I will not be the one to arrive at the answer, and none of my contemporaries will be the one to arrive at the answer. Maybe we will, but likely if we do find an answer, it will be only partially satisfying and it will just open up another question. And then that's okay. That we don't need to have all the answers, that the process of finding things out, the process of exploration, of being part of this journey that started roughly 400 years ago with the birth of modern science and stretches back millennia and hopefully will continue for centuries and millennia to come, to just be a part of that journey and to contribute to it in my own small way is humbling and liberating and something that brings a sublime sense of beauty to my life, and that there are mysteries that I will not be able to answer. I'm literally working professionally on a mystery that I will not be able to answer. So how can I hold the same standards to my everyday life? And that's part of the fun.
Do you think being married to someone in the arts helps balance your perspective?
Yeah. Oh, yeah. In fact, Kate, my wife, and I, she's the co-artistic director of Siren Modern Dance. And we actually met years and years and years ago. I was always interested in collaborating with artists. I love outreach. I love science communication. In fact, I spend more time in science communication than I do in my research. And I've always been wanting to reach new audiences. We actually met through a common contact. It turns out I was the only astrophysicist looking to partner with a dance company on something. And she was like the only dancer looking for a physicist to partner on a project. So of course we were going to find each other.
That's some destiny shit too, though.
I know, right?
Like how crazy.
How crazy. But then I have a feeling that no matter what path I took in life and no matter what path she took in life, that we would end up finding each other. It was just a matter of when. And we collaborated on a project that's still ongoing today. Then we fell in love and got married. And that project still exists. It's called TikTok, which is not, it was named before the explosion.
Invented TikTok?
Yeah. So, yeah. So big story.
Wow.
No. Yeah. We named it before the explosion of the social media platform.
Spelled the same way?
No, like traditionally, TICK,
Okay.
TikTok. It is a 45-minute exploration on the nature of time, where I narrate parts of it. And then there are large sections that are not narrated. It's set to Mozart. And it's a beautiful dance. It's a modern dance piece. We have performed it all around the world. We were fortunate enough to be selected as U.S. cultural ambassadors to the World Expo in Dubai last year, where we got to perform it on the world stage. We have brought it to audiences across the country. And it was originally, I approached artists as a way of bringing my science to new audiences. But then I watched and participated in this creation of this dance piece. And I realized I have a lot to say about time as a physicist. And then there's 2 narrative sections that I'm pretty proud of, where I talk about the science of time. But then there's a lot that I don't have anything to say about, that the dancers do, that the choreography does, that the music does. There are many human aspects of time and our experience of time and our relationship to time that myself as a scientist, as a physicist, I'm silent about. But the dancers were not. And Kate, the choreographer, was not. And so that started me on a journey of really expanding my views of what does it mean to answer these kinds of questions, and where do the answers come from? And can answers be felt but not said? Can they be experienced but not understood? And I feel, I'm asserting this, that I feel like I'm a more well-rounded scientist. I'm also not alone. Many scientists, many physicists love art, love music, love engaging with philosophy, love comedy, love movies, and use these as ways to understand the natural world and truly understand that science does not sit alone and should not sit alone. It is not separate. It is special, but so is music, so is dance, and so is art. These are all special in their own way and can inform our place in the universe and the nature of the universe and our relationship with it. And we can all sit around the campfire singing Kumbaya.
You must have been drawn to art as an exploration for science prior to meeting your wife, though, if you even were entertaining the idea of collaborating with dancers.
Yeah, at the time I was living in Columbus, Ohio. I had just finished, after I got my PhD in 2011, I went to Paris for 3 years and worked at the Paris Institute of Astrophysics. From there, I went to the Trieste Observatory in Italy, worked there for 2 years, then came back to the US, back to Columbus, near where I'd grown up, and had a position there. Started doing more outreach. I had my podcast, Ask a Spaceman, which was growing. And very early on, I have no artistic sensibilities whatsoever. I cannot sing. You do not want me to sing. I cannot dance. I cannot draw a stick figure. But I appreciate art. I like a good movie. I like a good song. I love a wonderful meal at a fancy restaurant. And so I don't know why. I cold emailed a dozen dance companies in Columbus. One of them got back to me, and we put on a production called Song of the Stars, an exploration of the life histories of the stars. We actually had it filmed and published on PBS member stations around the world. This is back in 2016, 2017. And I was looking for my next project. And independently, totally parallel and unbeknownst to me, Kate, who was living in Manhattan at the time, had, with her company, which they just celebrated their 20th anniversary season, had created a dance exploring quantum mechanics, superposition, entanglement, spooky action at a distance, all the rest. And they were touring it, and they had reached out to my boss at the time in the physics department at Ohio State University, saying, hey, it looks like you're hosting a conference later this year. We would love to come perform. And he said, sorry, we have no budget, but you should talk to Paul because he's into this sort of thing. And that's how we were introduced.
Oh, that's so cool.
And we started cooking up ideas and we decided to talk about time.
Wow. What an interesting hybrid. I mean, your kids are going to be so interesting.
Oh, they're bored by the whole thing. No, they'll show up at our performances grudgingly. But I encourage my children to follow their own passions, to follow their own dreams. I have no expectations that they should be a scientist, and she has no expectation that they should be dancers.
But just the upbringing and just the two different disciplines that seem starkly different on their face, but in reality could be sort of cousins or best friends even.
I mean, we're all human, right?
Yeah.
And we all are curious. We all move. We all have the foundations of science within us, which is a curiosity of the natural world. And we all have the foundations of dance within us. We all move. And if you put on a good song, we'll all start moving to it. So this is just different facets, different aspects of our fundamental humanity.
That's just such a cool way to look at it. But your kids inevitably, I imagine, will have this seared in their minds and some subconscious level, just having two parents in these seemingly oppositional careers. I just think will make an interesting, well-rounded person.
I hope so.
That's a really cool thing. Okay, I only have a couple more things for you, then I'll cut you loose.
Let's do it.
Okay. So relating to quantum mechanics, can you explain to me the physics community's acceptance of Brulé's pilot wave theory and what exactly that is and how that fits into quantum mechanics at all?
Yeah, absolutely. So quantum mechanics is a set, as currently formulated, is a set of mathematical equations that do a great job of explaining subatomic processes. It gets results. It is a machine that you plug in inputs and you get predictions that you validate against the experiment. It does a great job at that. It does a horrible job at actually explaining what is going on. It's like if I had a theory of planetary motion or orbits or the rising and setting of the sun that did not include planetary rotation or movement, where I can put in an input and get an output and validate against experiment, but I can't tell you what's actually happening.
Right.
So that's where we get into the world of what we call the interpretations of quantum mechanics, which are different mental pictures of what is actually happening at the subatomic world. And the most common interpretation is called the Copenhagen interpretation, which is basically shut up. Don't worry about it. It's not your business. Just let the electron do electron-y stuff and get results and then call it a day and be happy and thankful that we even got this far.
Right. Not very satisfying.
Not very satisfying, but still dominant because whatever.
That's what we have.
It's what we got. There are other interpretations. One of these is called the pilot wave interpretation, which was created by Louis de Broglie, who was one of the founders of quantum mechanics. And
De Broglie, that's what I meant to say.
Yeah. Or de Broccoli.
Yeah.
You know,
like
that's
de
what I
Broccoli.
called him in grad school.
Also
Still
Bohm
today.
too, right?
The what?
Bohm didn't BOHM. Wasn't he a scientist that like
Bohm.
Bohm.
Bohm. Yes. So it was created by de Broglie, who let's say had some interactions at conferences with people like Heisenberg and Bohr. We don't know exactly what those interactions entailed, except after those conferences, de Broglie dropped this hypothesis. So some say he was convinced, some say he was convinced to drop this. We don't know. It was picked up decades later by David Bohm who fleshed it out as a full interpretation of quantum mechanics. He said, okay, here's what's really going on. Here's what's going on. For every particle that you see, like an electron, and it's whizzing around, it's doing its thing, it's flying, it's bouncing, it's doing whatever electrons do. It has a wave attached to it. This wave travels like waves do. We call it a pilot wave. And waves do things like refract and diffract and do all sorts of complicated wavy stuff. And then the wave tells the electron what to do. We don't get to see the wave because it only talks to the electron. And so from our perspective, the electron is doing all this weird, random, literally random, subatomic stuff, but really everything's cool. Everything's fine. What appears random to us is just because we can't see the wave that is propagating and interacting in complicated ways. But it's really telling the electron what to do. And if we could see the wave, then we'd be like, duh, like this is so obvious. Right. This is all normal physics, just imported down into small scales.
The wave is piloting it.
Exactly.
Therefore,
it's telling the electron where to go. And so you don't need weird, wacky quantum mechanics full of probabilities and entanglement. You just have, I shouldn't have said entanglement because that comes back later. But you don't have these weird probabilities. You just have normal physics. Wave physics.
And everything's good.
Everything's cool.
Whew, thank goodness.
It is not widely accepted as a strong interpretation of quantum mechanics because for a couple reasons. One, the real nasty bit of quantum mechanics is not the probabilities, it's the entanglement. This spooky action at a distance. I have an electron, I secretly know.
This locality issue.
Pilot wave theory, all about non-locality.
Yeah.
Because I have my little wavy over here that extends the entire breadth and depth of the universe and interacts with that wave over there. And so you don't get rid of the real nasty thorn. The probabilities are annoying. Mm-hmm. The uncertainty results are annoying, but whatever, you can get around that. The entanglement is the real big thorny issue because that's what breaks non-locality. Breaks locality. And pilot wave theory is all about that. And then there are some other issues okay, you have these waves, but don't exist. They don't interact with anything else. So that's kind of weird. You're just kind of adding steps to the problem. And the waves affect the electrons or the particles, but the particles don't pilot the waves. And we know some things we've learned, for every action, there is equal and opposite reaction. That still holds at subatomic scales. It gets modified a little bit because quantum mechanics, but it still holds. But now we have a thing where the wave affects the particle, but the particle does not affect the wave. And so we have everything's fine. Classical physics is restored. Except for that major piece where every action does not have an equal and opposite reaction. So it solves some problems, or it neatly answers some problems with quantum mechanics, but then raises some others. And at the end of the day, you still end up with, the quantum world operates according to different rules. Sorry. Yeah. You just change which rules are violated and which are upheld.
Right. So it doesn't really solve anything. No. It just is these things are being piloted. There is a reason they are behaving in this way.
Yeah.
We just don't know what
these are, how they work, or
right. It just seems like you're kicking the
or why these rules apply to the subatomic world but not the macroscopic world. So quantum mechanics is like trying to hold on to a slippery bar of soap, because every time you try to clamp down on one set of questions, you just raise more. And no matter what interpretation you pick, you end up ultimately just saying, well, I guess the subatomic world is different.
Does it not follow to reason that is not, it doesn't go both ways in the sense with superposition, where you're observing an electron and it behaves in a way that is different than if it's not being observed.
Yeah.
But so if the macro world can affect the subatomic world through observation, does that go the other way also?
In terms of pilot waves, the problem is that the waves pilot the electrons, but then there's no equal and opposite reaction. The particles do not influence the motion of the wave. So you only have a one-way fundamental physical interaction, regardless of observation or not. You have waves influencing particles, but not particles influencing waves. And so you have to say, well, macroscopic rules don't apply, which is the problem we started with.
Right. And what about string theory? Where are these strings?
Oh gosh, string theory.
This is not widely accepted either, it seems like.
Unfortunately, no. And string theory is one of these ideas that would be great if it were right, but it appears to be incorrect. And we have sunk decades of work into string theory. The problem with string theory, twofold. One is when we say something like we can't test string theory. It's not because we don't have a powerful enough experiment. If we had a particle collider the size of the orbit of Jupiter, or that swung around the entire Milky Way galaxy, where we access the most unfathomable energies imaginable, we could not test string theory, because string theory makes no predictions. String theory is incomplete. String theory has not been solved. String theory, as we currently understand it, cannot make predictions about the physical world. And if you can't make predictions about the physical world, you can't validate against experiment, you can't test the idea. Testing string theory is not a question of having powerful enough experiments. It's about not having a powerful enough theory.
Right.
String theory is not yet a theory of physics. It hopes to be a theory of physics someday, but it's not. It can't make predictions. So even if we had a super powerful collider, I couldn't tell you if string theory is right or not, because string theory makes no predictions that we can test.
So why does it have such a foothold within the physics community?
Oh, who knows?
Why do I know about it as a layperson?
Because Brian Greene wrote a really famous book about it.
Mm.
And Brian Greene wrote a really famous book about it because it was the dominant paradigm in high energy physics and super theoretical circles for a few decades, because it seemed like it was the best, and it was the best idea we had in the 80s and 90s. And so that attracted theorists to keep working on it. And it always seemed like right around the corner, we would crack it and we would be able to produce a theory that could give us verifiable results. And it has felt like the true answer has been right around the corner for like 30 years now. But the other problem with string theory is that many parts of string theory are predicated on something called supersymmetry, which is a highly theoretical idea that connects basically all particles in the universe with partner particles that have yet to be observed. The Large Hadron Collider at CERN in Switzerland, or the Swiss-French border, was built starting 20 years ago with two goals in mind. One, which was to find the Higgs boson, cornerstone of the standard model of particle physics. And two, to find evidence for supersymmetry. Found the Higgs boson like right away. Nobel Prize, good job. To date has found zero evidence for supersymmetry. And in fact, as it continues not finding evidence for supersymmetry, almost all models of supersymmetry, versions of it, variations of it have been ruled out. And without supersymmetry, it's not clear that you can have string theory.
And what exactly is supersymmetry?
Supersymmetry is this idea that there are two different kinds of fundamental particles in the universe. There are, and I'm sorry, we get into jargon land. This is high energy physics. It's just all jargon all the time. We have bosons and we have fermions. Bosons are like the force carriers. These carry the strong force, electromagnetic force. And then we have the fermions, which are the building blocks. These are the electrons, the quarks, the neutrinos. And these particles look very, very different to each other. It's these two fundamental classes. Supersymmetry says they're actually connected to each other, and they're actually mirrors of each other, but not in a very obvious way, that they're actually particles, more bosons and more fermions that we have not yet observed that match with each other. So for an electron, there is a supersymmetric partner called the selectron. And for the quark, there's a supersymmetric partner called the squark. And for the photon, there's a supersymmetric partner called the photino. And my absolute worst favorite is the supersymmetric partner of the W boson is called the Wiener boson. I'm sorry, everybody. I apologize.
We're going to bleep that because it's disgusting.
It's horrible. It's a slur in some languages.
It should be.
We have not yet detected selectrons or squarks or photinos because they're really heavy. And so they decay really quickly. So we need super powerful particle colliders to create them and detect them. So we created the super powerful particle colliders and we did not create any. There are none. So almost all supersymmetric models are wiped off the map because we do not see these. Without supersymmetry, it's not exactly clear that you can have a string theory. Because string theory is based on supersymmetry. So string theory is on a really shaky experimental ground. Even though it doesn't make any direct predictions itself, we are able to like look at the foundations of string theory, and it turns out those are all rotten. So it's not exactly clear we can build the house. That hasn't stopped string theorists from continuing to try to build string theory, which is good for them. Also because when you invest a quarter century in an idea, it's kind of hard to pivot.
Yeah, that sunk cost fallacy is very sunken. Interesting. So then the evidence of these things, these squarks and all this stuff.
Selectrons and photons and we know bosons.
So have they been ruled out to not, the supersymmetry, has it been ruled out to not exist, or has it just not had evidence to prove it does exist?
Many models. So supersymmetry is like a family of ideas, a collection of ideas. And in these collections, these selectrons and squarks can have different masses and different properties. Most models of supersymmetry are hard ruled out, are just gone because they should have been there. There are some corners of supersymmetry that are much, more tangled, much more non-intuitive, not really very viable, where they can skirt by like, oh, you didn't see this electron because it had this kind of property. And so, oops, you just missed it. Okay. Like, that's kind of tough.
Yeah.
Like, that's tough.
Yeah. Okay. That makes a lot more sense. Are there any other interpretations of quantum mechanics that we haven't discussed or that are taking foothold in the physics community that you think are interesting?
String theory isn't necessarily an interpretation of quantum mechanics. It's an attempt to marry quantum mechanics with gravity because we do not have a quantum description of gravity, and we really wish we did. Even if we had a string theory, we would still need an interpretation of quantum mechanics itself. Like these are two separate questions.
I see.
There are other attempts to interpret quantum mechanics, like the many worlds interpretation, where the universe keeps branching off from each other, from itself, every time there's a quantum interaction. Ultimately, at the end of the day, you just have to say, well, the subatomic world is different. And it behaves differently no matter what. You always have to say that. And then there are other attempts to marry quantum mechanics with gravity. There's an attempt called loop quantum gravity, which is also a tangled mess that has failed to produce any predictions. So, like, we're kind of stuck.
Interesting. Okay.
It's a tough time.
The last thing I'm curious about, maybe not the last thing, the last thing for today, for this volume, is black holes. We're talking about gravity. So the idea of a black hole and a white hole are fascinating concepts, and again, like brain-breaking ideas, right? Like Big Bang, quantum mechanics, expansion of the universe, black holes. To me, I'm like, this is just the pinnacle stuff. The pinnacle of like, how can nothing escape? What is it?
Yeah.
Where does it come from? Are we orbiting a black hole? Are there multiple black holes? What happens when a black hole goes inside a black hole? So,
all right.
Where do we start?
When a black hole meets a black hole, you just get a bigger black hole. Their singularities merge, and you end up with a bigger black hole. What else? White holes don't exist.
Really?
Sorry.
At all?
Yeah, no, they're unstable, catastrophically unstable. As soon as one little particle or photon approaches them, the whole thing blows up. So you don't get to have white holes in this universe.
To me, the idea of a white hole is this thing that it is perhaps the mirror and opposite of a black hole, that as things are being sucked into the black hole, the white hole is sort of blasting things into a different universe.
Yep, and that was a very early interpretation. We call this an Einstein-Nordstrom wormhole, actually, where you have a black hole and a white hole connected by their singularities. But the problem is white holes, everything always exits a white hole. You cannot enter a white hole, but they're still massive. They still have gravity. And so you can bring an object, you imagine random little particle floating near a white hole. It's attracted by the gravity of the white hole, so it starts getting closer and closer and closer, but it can't go through the event horizon. It can't enter. So the energy of this system goes up and up and up and up as it gets closer and closer to the event horizon of the white hole. And then the energy goes to infinity and the whole thing blows up. White holes are fundamentally unstable objects, which means they don't get to live very long in this universe, even if you were to make one.
So do they exist, but they don't last very long, or have they never existed? Or can we not answer that?
Something that is unstable, like a random quantum fluctuation in space-time, will kill it. Mm-hmm. So even if there were some mechanism to form white holes, they would immediately pinch off.
That makes sense. So now, how are black holes formed in the first place? Is this a tearing of the space-time fabric?
No, it's more of a compression, actually. It's more of a squeezing of space-time. You can form black holes in surprisingly easily. The universe really enjoys making black holes. And the easiest way is to take a giant star, somewhere 8 to 10 times more massive than the sun, and compress it. Just squeeze it. Just turn off the lights, turn off the fusion reactions, let it die. And then the gravitational weight of that star will compress the core. And eventually the gravity becomes so strong that it overwhelms every other force. There's nothing that stops it. And so the star just collapses and collapses and collapses inwards on itself to essentially infinity. The star becomes infinitely tiny. It becomes a point in space-time. It becomes what we call a singularity. That singularity is surrounded by what we call an event horizon, which is a one-way boundary. You enter the event horizon, you cannot leave. Black holes are everywhere. There are billions of them in the Milky Way galaxy alone.
Billions?
Billions and billions of black holes.
Wow. And why don't they just suck everything up into it if light can't even escape?
Light can't escape. So black holes, say you have a black hole with a mass of 10 suns. It has the exact same gravity as a star with a mass of 10 suns. If you were to replace our sun with a black hole with the exact same mass, the object itself would only be about the size, it'd be smaller than Manhattan, but it'd have the same mass as our sun. So the Earth would stay in orbit.
Wow.
Because the gravity is the same. Black holes do suck on their surroundings, but so does the Earth, so does the sun. That's what gravity does. And the strong gravity only it reaches out to a certain distance.
Wow.
So yeah, things would be a lot darker, but our orbit would remain unchanged.
Probably freeze to death.
Yeah, there's that.
But we would still be orbiting, and all the other planets in our solar system would equally be unchanged.
Exactly.
Wow, that is so fascinating. Now, the idea of a wormhole, is that in any way connected to a black hole?
Yes. So wormholes are another hypothetical idea that are also catastrophically unstable. If you take a black hole and a white hole, for example, and kiss their singularities, you can form a wormhole that is unstable. The moment a single photon, a single particle tries to traverse the wormhole, it will tear itself apart faster than the speed of light. The only way that we know of to stabilize a wormhole is to thread it with matter that has negative mass, something we call exotic matter, like something that weighs -5 pounds. As far as we know, no such thing exists. And so as far as we know, it is impossible to stabilize a wormhole.
Interesting.
Like I said, anti-therapists, I just kill dreams.
Yeah. So a wormhole is a theoretical idea, but can't exist in reality.
As far as we understand.
Oh, interesting. Okay. And then how does dark matter and dark energy fit into this?
Different questions.
It's a separate idea.
Yeah, dark matter is, we see evidence for dark matter everywhere in cosmology. It turns out most of the matter in the universe is invisible. Who knew? We sure didn't. But the universe is under no obligation to make matter in the universe like interact with light. It just turns out that's the dominant component. We do not know the identity of dark matter. We do not know what kind of particle it is. It is currently unknown to particle physics and modern physics, but it's out there and we're trying to hunt for it. Dark energy is a completely different phenomenon, which we discovered in the late 1990s, where it turns out that the expansion of the universe is accelerating. Not only is the universe getting bigger, it's getting bigger and bigger, faster and faster. We have no idea why. Straight up. We got a cool name for it, though. Dark energy. Great branding.
Yeah.
But we don't know what's causing it.
And how do we discover that it was expanding at an increasing rate?
We discovered it initially through observations of distant supernovae that were far dimmer than they should have been based on standard calculations of the expansion rate of the universe. And the only interpretation we had for that was that the expansion is accelerating. Nowadays, that was 25 years ago. Nowadays, we have multiple independent lines of evidence that all point to an accelerated expansion of the universe.
And what are the implications of that? If you have a universe that is accelerating in its expansion?
That means that hold on for dear life, because the Milky Way and our nearest neighbors, Andromeda, Triangulum, a collection of galaxies we call the local group, we are gravitationally bound. We're all glued together with our own mutual gravity. Over the course of the next 10 to 20 billion years, every single galaxy outside of our local group will eventually be torn away from us, and we will be alone in our pocket of the universe.
Wow. So it will become increasingly less likely that we interact with intelligent life as we're getting ripped away from...
Yep. Our observable universe grows smaller with time.
Will there be less stars? Will there be a tangible difference in like optically? Or fewer stars?
Not really, because all the stars we see in the night sky are no more than, I think the most distant one is 1,000 light years away, maybe even less. And we're talking about millions of light years distance to the nearest galaxies. But on the other hand, there's only so much gas and dust, stuff available for making stars inside of a galaxy. Eventually, our galaxy will run out of material. And in about 10 trillion years, plus or minus, the last star will be born.
Interesting. So if we know that the universe is expanding at an accelerating rate, do we know the expansion point from whence it starts?
The accelerated expansion started about 5 billion years ago. As far as the starting point of expansion itself, it's everywhere. The Big Bang happened right here in this room. It happened in the Andromeda Galaxy. It happened throughout the entire universe.
So the expansion point is from all of it.
Exactly. The universe is expanding away from itself. From our perspective here on the Earth, it looks like every galaxy is receding away from us. But if you could magically transport to any one of those galaxies, it would look like the universe is expanding away from you.
And is that, are we not able to conceptualize that because it is, I guess as humans, we understand things on like a 3-dimensional plus time fabric, whereas in space, it's not operating?
It is operating 3-dimensionally, but we're used to thinking of 2-dimensional objects, like the surface of a balloon expanding in 3 dimensions. Our universe is simply a 3-dimensional object that is expanding in 3 dimensions. And that is very, very hard for our tired monkey brains to figure out.
Fascinating. Last question. Time travel. I know we talked about forward time travel. You can go forward, you can go back. I know people have hypothesized with wormholes, black holes, that time travel is potentially possible. Do you think that, and when I say time travel, I mean backwards.
Into the past. The interesting kind of time travel.
Exactly.
Yeah, the cool one.
Do you have any thoughts on that, or is there any credence to that idea?
As far as we can tell, time travel into the past is forbidden. Every time we try to concoct a device or a mechanism or a theory that allows backwards time travel, some rule of the universe comes to slap our hand away from the cookie jar. That said, we don't understand why. There is no universal law. There's no equation that I can print on a t-shirt that says this is why time travel is forbidden. But it appears to be so. And we don't understand why.
So I guess we just have to rely on forward time travel.
Yeah, or keep pushing the boundaries. Like, if we keep investigating reverse time travel, either we'll figure out how to do it, which will lead to a revolution in understanding of physics, or we'll understand why it is truly forbidden, which will lead to a revolution in our understanding of physics.
Right.
Either way, there's learning.
It's the end of all of it, huh? There's just learning.
There's just learning. That's the great part about science, is no matter what answer you get, you always learn something.
Yeah. It is a fractal, ultimately. It is a tree, of questions.
Knowledge within knowledge within knowledge, and questions within questions within questions.
Fascinating. And is the universe a fractal is one of the questions that you answer on Ask a Spaceman?
In some scales, yes, but largely no.
Okay. You have very many other questions that you answer that I love. Another one that I saw was, if the sun is dying, it's decaying, can we move the Earth to save humanity on Earth? You don't have to answer it now. Okay. I think if people are interested in watching it, they should go to your channel and they should check it out.
All right.
Thank you so much for answering all my questions.
Oh, this was so much fun.
I really appreciated it. I assumed that there would come a point where you'd be like, all right, we got to go. And it never happened.
What time is it? I have no idea.
I have no
Is
clue.
it tomorrow already?
It might be. What is time?
Did I miss my last train?
What is time, dude?
Yes.
Who has any idea? Dr. Sutter, thank you so much. I really appreciate this.
This was a joy. Thank you so much.
Thank you. I can't wait to talk more next time.
Next time.
Peace.